Are you preparing for the Google Certified Associate Data Practitioner certification exam and looking for a complete study resource? Then you're in the right place. In this video, we'll go through a full crash course covering the key concepts, skills, and exam topics you need to know to confidently pass the certification exam. Plus, I've included 100 practice questions and answers to help you test your knowledge and understand the types of questions you may encounter in the real exam. Whether you're a beginner starting your data journey or an IT professional looking to validate your skills, this course is designed to help you prepare efficiently and effectively. And that's not all. A PDF study guide is also available, allowing you to review the material offline and continue your preparation anytime, anywhere. Before we get started, make sure to subscribe to Tech with Shapingpixel. Turn on notifications so you never miss future certification courses. Visit www.shapingpixel.com for study materials, practice exams, and certification resources. Let's begin our journey toward becoming a Google Certified Associate Data Practitioner.
This course is designed for anyone interested in learning more about GCP. You do not need any previous experience with Google Cloud Platform to get started. However, having some general technical knowledge will be helpful, since basic terms like file server or operating systems are not explained. The best way to learn is by doing. You are encouraged to try out the task yourself using your own GCP account. If you do not already have an account, you can easily create a free trial account to follow along. By the end of this course, you should be able to describe some of the services available in GCP across various categories. If you are ready to discover what you can do with Google Cloud Platform, let's get started.
Overview of Google Cloud Platform.
Let's do a quick overview on Google Cloud Platform or GCP, which is a suite of online services that help organizations build, host, and deliver applications. By running in Google's global data centers, GCP lets you leverage Google's network and expertise, while only paying for what you use. GCP offers several ways to run your applications. Compute Engine provides virtual machines or VMs for traditional workloads. App Engine is a platform as a service that lets you upload code and forget about infrastructure. For lightweight portable deployments, containers are supported through Cloud Run for single containers and Google Kubernetes Engine or GKE for orchestrating multiple containers. Cloud Functions enables event-driven serverless computing for individual functions. Google Storage is GCP's object storage, ideal for files like images and videos, with 4 classes: standard, nearline, code line, and archive. Each offers immediate access at different price points. For traditional file storage, FileStore provides NFS compatibility file shares. Cloud SQL manages MySQL, PostgreSQL, and Microsoft SQL Server database. For NoSQL needs, options include Bigtable, FileStore, and Firebase real-time database. Cloud Spanner unequally combines scalability with relational features, while BigQuery serves as a powerful data warehouse. GCP Virtual Private Cloud or VPC connects your resources securely. You can link VPCs, assign IP addresses, and use Cloud VPN or Cloud Interconnect for secure connections to on-premises networks, ensuring flexibility and reliability for your applications. So migrating your server applications to Google Cloud Platform or GCP is easier than you might think. The simplest way is to move your app to a virtual machine, often called a VM on GCP. To get started, open the Google Cloud Console in your browser. No installation needed. Head to the menu, select Compute Cloud, and click Create. Name your VM, keeping in mind that Google calls these instances. Choose a region and zone close to your users for best performance. Each region has multiple zones, which helps keep your app running even if one zone fails. Next, pick up your machine type. General purposes is balanced choice, but you can select memory optimized or compute optimized if needed. Choose your processor series like Intel or AMD, or stick with the default E2. Then select the VM size. Shared core options are cheapest, while standard high memory and high CPU offers more resources. Set your boot disk, select an operating systems like Debian and adjust the disk size. For web servers, open HTTP and HTTPS ports. Consider preemptible instances for big savings, but remember they can be stopped anytime. When finished, click Create and explore your new VM. Don't forget to delete it when done to avoid any charges.
Google Cloud Platform, or GCP, offers a wide range of services beyond just compute, storage, and networking. Let's highlight some of the most important tools that help organizations move to and thrive in the cloud. Many organizations start by migrating existing systems. Google Cloud VMware Engine lets you run VMware environments directly on GCP. Migrate for Compute Engine helps move virtual machines from VMware, Amazon Web Services, or Microsoft Azure, while Migrate for Anthos converts virtual machines into containers managed by Google Kubernetes Engine. Google leads in artificial intelligence and machine learning. Services like Vision API detect objects and images, Translation API supports over 100 languages, and Dialogflow builds advanced chatbots. For custom needs, AutoML and AI Platform let you train and deploy your own models. GCP's analytics tools cover ingesting, storing, processing, and visualizing data. PubSub handles streaming data, BigQuery enables interactive analytics, Dataflow processes data, and Looker or Data Studio visualize insights for your business. Cloud Build automates building and deploying applications, integrating with repositories like GitHub. For global performance, Cloud CDN speeds up content delivery, and Cloud Load Balancing manages traffic spikes seamlessly. Security is central. Identity and Access Management, or AAM, controls permissions. Cloud Key Management and Secret Manager protect sensitive data, while Data Loss Prevention helps safeguard personal information. These highlights just scratch the surface of GCP's capabilities. Explore Google Cloud's Products page or search the console for even more solutions tailored to your needs. Let's explore how to create a complex solution using Google Cloud Platform, or GCP. With so many services available, you can build anything from a simple website to a robust, scalable application. For a basic static website, you can just upload your files to cloud storage and update your DNS records. But if you need more flexibility, Compute Engine is your go-to. Compute Engine lets you run custom configurations, including Windows or specialized Linux setups, which App Engine cannot support. Distributing your instances across multiple zones ensures your site stays up, even if one zone fails. Expecting high traffic? Set up auto-scaling and place a global load balancer in front of your instances. To protect against distributed denial of service attacks, add Cloud Armor. This combination keeps your application responsive and secure. Store static files like images and HTML in cloud storage and speed up delivery with Cloud Content Delivery Network. For dynamic content, use back-end app servers behind an internal load balancer, storing data in Cloud SQL or Firestore depending on your needs. You can use Cloud DNS or your existing DNS provider. With GCP, building complex, reliable solutions is within reach. Once your applications are running on Google Cloud Platform, or GCP, keeping them healthy is essential. Google's Cloud Operations Suite, previously called Stackdriver, is designed to help you manage and maintain your cloud resources efficiently. Cloud monitoring provides a comprehensive overview of your resources. You get real-time graphs for metrics like CPU utilization, response latency, and network traffic. You can also build custom dashboards. Most importantly, you can set up alerts such as uptime checks to notify you if a virtual machine goes down. Cloud logging acts as a central hub for all your resource logs, making it much easier to search and troubleshoot issues across your environment. The suite also includes tools like error reporting, CloudTrace, Cloud Debugger, and Cloud Profiler. These help you debug live applications and track down performance bottlenecks quickly. Security Command Center brings security and compliance monitoring together. Its dashboard highlights active threats and vulnerabilities, such as cross-site scripting risks, and tracks compliance violations like PCI DSS issues in your GCP environment. For automation, Cloud Deployment Manager lets you define and deploy multiple resources at once using configuration files, streamlining resource creation and management. Google Cloud Platform, or GCP, is a suite of online services that help organizations build, host, and deliver applications using Google's global data centers. With GCP, you can access powerful computing, storage, networking, and artificial intelligence tools, all managed by Google. GCP's main compute options include Compute Engine for virtual machines, App Engine for web and mobile apps, Cloud Run and Kubernetes Engine for containers, and Cloud Functions for running individual functions. App Engine, Cloud Run, and Cloud Functions are called serverless, meaning you do not manage the underlying infrastructure. Compute Engine also offers preemptible instances, which are virtual machines that cost about 70% less, but can be stopped at any time. For storage, GCP provides cloud storage for unstructured data and file store for file sharing. Relational databases include Cloud SQL and Cloud Spanner, while Bigtable, Firestore, and Firebase Real-Time Database handle NoSQL needs. Memory Store is used for caching data. GCP's Virtual Private Cloud, or VPC, connects resources securely. Cloud VPN and Cloud Interconnect link your on-premises network. Identity and Access Management, or IAM, controls user permissions, and everything is encrypted by default. BigQuery powers analytics, while Dataflow and Dataproc manage data processing. For artificial intelligence, GCP offers APIs for vision, language, and conversation, plus AutoML for custom models without coding. Setting up a Google Cloud Platform environment. Now let's guide you through creating and managing cloud projects. While admin access to a Google Cloud Platform account is helpful, it is not strictly required. First, create a new project in your Google Cloud Platform dashboard. Give it a clear name and set up your organization. This helps keep your resources organized and secure. Next, add users to your project. Assign appropriate permissions to each user, ensuring they have access only to what they need. Enable necessary application programming interfaces for your project. Set up budgets and monitor spending. Before you can build anything on Google Cloud Platform, you need a project. Projects help you organize all your resources, like compute, storage, and networking, under one roof. Every resource must be assigned to a project. Projects keep things tidy. Each project has its own users, application programming interfaces or APIs, and billing information. This makes it easy to separate, for example, your personal blog from your work website and helps prevent confusion between development and production environments. To create a project, log into the Google Cloud Platform console. Click the project selector at the top, then choose New Project. Give your project a descriptive name, like Photoblog, and let Google generate a unique project ID for you. Remember, the project name is just the label and can be changed anytime. The project ID, however, is globally unique and permanent. It is best to let Google generate this for you. When you delete a project, all its resources are deleted too. Projects are marked for deletion for 30 days, giving you time to restore them if needed. Managing user accounts and permissions in Google Cloud is essential for keeping your projects secure and organized. Each project has its own set of users, and every user can have unique permissions based on their responsibilities. You can manually add users if your team is small, but for larger organizations, automation is key. Tools like Google Cloud Directory Sync let you replicate users from systems like Active Directory or LDAP into Google Cloud Identity. Cloud Identity helps you manage accounts across multiple projects, supports single sign-on with Security Assertion Markup Language 2.0, and offers multi-factor authentication for added security. Permissions are managed by assigning roles to users. Instead of giving individual permissions, you assign a role, which is a group of permissions. This makes managing access much easier and more consistent. Always double-check you have the right project selected before granting access. Then assign roles based on what each user needs to do. There are 3 main types of roles: basic, predefined, and custom. Basic roles are broad. Predefined roles are more specific, and custom roles let you tailor permissions exactly as needed for your organization. To create custom roles, select permissions that fit your needs. Removing users is simple. Just select them and click Remove Access. Understanding these tools helps keep your cloud environment secure and efficient. Google Cloud APIs, or Application Programming Interfaces, are tools that allow your projects to interact with specific Google Cloud services. While some APIs are enabled by default, many require you to turn them on before use. Enabling an API grants your project access to that service, like the Google Calendar API for managing calendar events. Disabling APIs you do not need helps protect your project and control costs, since you cannot be charged for services you cannot use. To enable an API, first make sure you have selected the correct project. Then navigate to APIs and Services and choose Enabled APIs and Services. Click the Enable APIs and Services button, search for the API you need, and click Enable. Some APIs may require extra steps, such as accepting a terms of service or creating credentials. You can confirm the API is enabled by checking the Enabled APIs and Services page. If you no longer need an API, select its name, click Disable API, and confirm. The API will be removed from your enabled list, improving security and reducing unnecessary costs. Only enable APIs your project truly needs. This keeps your project secure and cost-effective, ensuring you only pay for what you use. Signing up for Google Cloud Platform, or GCP, requires a credit card, but you get a free trial with $300 in credit for 90 days. There is also a free tier with limited access to certain services. Eventually, though, you will start incurring charges, especially when running production workloads. To manage billing, click on Billing in the navigation menu. Here, you can view charges and switch between billing accounts. Each billing account is tied to a specific credit card or bank account. If you want different projects billed to different cards, create additional billing accounts and link them to your projects. Budgets in GCP help you monitor spending, but they do not cap it. Set a budget by naming it, choosing a time range, and specifying an amount. You will receive alerts at thresholds like 50, 90, and 100% of your budget. Customize notifications to ensure you never miss an alert. For detailed charge analysis, set up a billing export to BigQuery. Choose between standard, detailed, or pricing exports. Once configured, you can use BigQuery to filter and analyze your spending data for deeper insights. Remember, disabling billing does not stop all charges. Deleting the project is the only way to guarantee no further costs. Always monitor your spending closely. Setting up a Google Cloud Platform environment starts with creating and deleting projects. Projects are essential for organizing and managing all the resources in your Google Cloud Platform account, keeping everything structured and easy to control. Next, you need to create user accounts and assign them permissions using roles. There are 3 types of roles: basic, predefined, and custom. Basic roles are straightforward but not secure for production environments. Predefined roles offer more specific permissions, making them a better choice when available. If you need something unique, you can create custom roles. It is highly recommended to avoid basic roles and use predefined or custom roles instead. After setting up roles, enable the necessary Application Programming Interfaces, or APIs. APIs let your project access Google services like compute, storage, and networking. By enabling or disabling APIs, you control which resources your project can use. Adding a billing account is the next step. Billing accounts determine how you pay for services in each project. Projects can share billing accounts or have separate ones. You can also set up budgets and generate billing exports to monitor and analyze your spending. That covers the essentials of setting up your Google Cloud Platform environment. If you have questions or feedback, let us know and explore our other videos for more tips. Designing a Google Cloud infrastructure. Welcome to Designing a Google Cloud Infrastructure. In this video, you will learn how to build an enterprise IT solution using Google Cloud Platform, or GCP. To get the most out of this guide, you should already be familiar with the core components of GCP. We will use a case study to demonstrate how to apply enterprise principles to your cloud design. The process begins by taking your organization's requirements and translating them into the right compute, storage, and network components on Google Cloud Platform. You will see how to assemble these building blocks to create an enterprise-class application architecture that is both robust and scalable. High availability will also be a key focus, ensuring your solution remains reliable. Next, we will cover how to secure your environment. This includes authenticating users and applications, assigning permissions, encrypting your data, and meeting strict security standards such as the Payment Card Industry Data Security Standard, or PCI DSS. You will learn best practices for protecting your cloud resources and maintaining compliance. Finally, we will discuss designing a solution that can recover from disasters, ensuring business continuity. We value your feedback, so please rate this course when you finish. Thank you for joining us on this journey into Google Cloud infrastructure design. Great Insight is a company offering web-based interior design software with both subscription and ad-supported free versions. After 5 years of steady growth, they have secured new funding and are now expanding rapidly, especially in North America. Their technical environment started with Microsoft systems, but now mainly uses a LAMP stack. The only Microsoft components left are for payment processing and Active Directory. Their databases include MySQL for the main application, Microsoft SQL Server for payments, and a NoSQL database in development.
All systems currently run in a single data center. With growth accelerating, Great Insight faces several challenges. They need to scale quickly, improve reliability, and enhance security. Their disaster recovery plan is slow, and their infrastructure cannot keep up with demand. They must also maintain PCI DSS compliance for credit card processing, which is handled by a certified payment processor. The company's main goals are to move as much infrastructure as possible to the cloud, connect their data center to the cloud securely, encrypt all data, and design for high availability. They also want to reduce disaster recovery time from a day to just a few hours. By migrating to the cloud, Great Insight aims to boost performance, reliability, and security while reducing management overhead and preparing for future global expansion. When choosing compute options on Google Cloud, you are not limited to virtual machines. Let's quickly break down the main choices: App Engine, Kubernetes Engine, and Compute Engine. App Engine is perfect for new applications where you do not want to manage infrastructure. It automatically scales resources for you. However, migrating existing apps can be tricky, especially if they rely on unsupported languages or operating systems. Kubernetes Engine is ideal if your app already runs in containers, like Docker. It offers flexibility and scaling, but you need to configure it yourself. It is not suitable for apps that require specific operating systems, such as Windows. Compute Engine gives you the most flexibility. It is best for existing applications, especially those that need specific hardware, operating systems, or cannot be containerized. However, it requires more management than the other options. For our case study, Great Insight needs machines with specific vCPU and memory requirements. Google offers predefined and custom machine types, plus flexible licensing for Windows and Linux. You can use Google's pay-as-you-go licenses or bring your own. On Google Cloud Platform, or GCP, you have several storage choices for your instances. Standard persistent disks are affordable but slower, using magnetic drives. Balanced persistent disks use solid-state disks, or SSDs, offering a good mix of speed and price. Performance persistent disks are even faster, while extreme persistent disks target high-end databases. Hyperdisk provides configurable performance, and local SSDs deliver the highest speed, but are temporary and risky for important data. For most workloads, balanced persistent disks are ideal. They're faster than standard persistent disks and cost less than performance persistent disks. Plus, they're redundant, so you don't need mirrored disks. Database services on Google Cloud Platform. Cloud SQL is a managed relational database for MySQL, PostgreSQL, or Microsoft SQL Server. Firestore and Bigtable are NoSQL options, with Firestore excelling at simple, scalable data and Bigtable handling massive datasets. BigQuery is a data warehouse for analytics, while Cloud Spanner combines relational structure with horizontal scalability. For Great Insight's MySQL and SQL Server databases, Cloud SQL is the best fit, reducing management overhead. For their experimental NoSQL data store, Firestore is recommended, especially alongside App Engine for optimal integration. On Google Cloud Platform, or GCP, you have several storage choices for your instances. Standard persistent disks are affordable but slower, using magnetic drives. Balanced persistent disks use solid-state disks, or SSDs, offering a good mix of speed and price. Performance persistent disks are even faster, while extreme persistent disks target high-end databases. Hyperdisk provides configurable performance, and local SSDs deliver the highest speed, but are temporary and risky for important data. For most workloads, balanced persistent disks are ideal. They're faster than standard persistent disks and cost less than performance persistent disks. Plus, they're redundant, so you don't need mirrored disks. GCP offers 5 main database services. Cloud SQL is a managed relational database for MySQL, PostgreSQL, or Microsoft SQL Server. Firestore and Bigtable are NoSQL options, with Firestore excelling at simple, scalable data and Bigtable handling massive datasets. BigQuery is a data warehouse for analytics, while Cloud Spanner combines relational structure with horizontal scalability. For great insights, MySQL and SQL Server databases, Cloud SQL is the best fit, reducing management overhead. For their experimental NoSQL data store, Firestore is recommended, especially alongside App Engine for optimal integration. Google Cloud Networking is built around virtual private clouds, or VPCs, which are simply called networks. These networks help connect and isolate resources, making it easier to manage everything from small projects to large organizations. Resources are organized into projects, which act as boundaries for security and billing. Each project comes with a default network, but you can create up to 5 networks per project or request more if needed. Networks are unique to each project and cannot be shared directly. Networks span all regions, but subnetworks or subnets are regional. Subnets group resources and define IP address ranges. Instances within the same network can communicate, even across subnets, thanks to automatically created routes. Subnets must use non-public, non-overlapping IPv4 addresses. Default networks include firewall rules that allow internal traffic and specific protocols like SSH and HTTP. New networks start with no firewall rules. Instances need external IP addresses to reach the internet, and static IPs are only charged when unused. Private Google Access lets VMs use internal IPs for Google services. To connect your company's network to Google Cloud, options include Cloud VPN, Cloud Interconnect, and peering. For most needs, Cloud VPN with Cloud Router is recommended, as it dynamically updates routes and securely links your on-premises network to Google Cloud. Securing access to your Google Cloud infrastructure starts with strong user authentication. By default, Google Cloud Platform requires a Google account. But as your team grows, managing individual accounts quickly becomes unmanageable and insecure. To streamline access, organizations should use a centralized identity management solution. Google Workspace, which you might already use for tools like Google Docs, can also manage Google Cloud identities. If you do not have Google Workspace, Cloud Identity is a similar option built on the same platform. Most organizations already maintain a user directory, such as Active Directory or an LDAP server. The best practice is to synchronize this existing directory with Google Workspace or Cloud Identity. Google Cloud Directory Sync, or GCDS, is the simplest way to do this. GCDS copies users, groups, and other data from your directory to Google Cloud, running securely inside your network. Remember, synchronization is one way and must happen regularly. To make authentication seamless, implement Single Sign-On, or SSO. Google Cloud supports SAML 2.0 based SSO, allowing users to log in once and access everything. If your system does not support SAML 2.0, third-party plugins are available. For example, if you have Active Directory, use GCDS for synchronization and enable SSO. This ensures secure, efficient, and user-friendly access to your Google Cloud infrastructure. To manage access in Google Cloud, you assign roles to users, controlling what they can do with resources. Roles determine permissions, and you can assign them at the organization, folder, project, or resource level. There are three basic roles: owner, editor, and viewer, which apply at the project level. For more specific needs, Google Cloud offers predefined roles, which provide fine-grained access to individual resources. For example, the Cloud SQL Viewer role allows read-only access to Cloud SQL resources. When a user has roles at different levels, their permissions combine. For instance, if Marie is a viewer at the organization level and an editor at the project level, she will have editor permissions for that project. Follow the principle of least privilege. Only grant the permissions necessary. Assign roles to groups instead of individuals for easier management and consistent privileges. Control who can add group members or change policies, and always have more than one owner. A network administration group might get the compute network admin role. A QA team could have editor access on test projects and viewer access on production, or receive several predefined roles. Regularly audit policy changes using cloud audit logs to ensure security and compliance.
When building applications on Google Cloud Platform, or GCP, you need a secure way for your apps to access the services they depend on. That is where service accounts come in. They help you avoid embedding credentials directly in your code. A service account in GCP is a special identity with its own email address and a public and private key pair. When your application runs, it uses this identity to prove who it is to other GCP services, like Cloud SQL or Cloud Storage. By default, virtual machine instances use the Compute Engine default service account, which has limited permissions. For example, it can only read from cloud storage, not write. To give your application more access, you need to assign the right roles to its service account, such as the Cloud SQL Instance User role. For example, if your Tomcat or IIS instances need to talk to a Cloud SQL database, you must create service accounts for them and grant the necessary permissions. The load balancer and web instances communicating over HTTPS do not require service accounts. As your architecture grows, you may need more service accounts. For now, understanding these basics will help keep your GCP application secure and well managed.
Protecting data starts with controlling who can access it. On Google Cloud Platform, or GCP, you have several options: identity and access management permissions, access control lists, signed URLs, signed policy documents, and Firebase security rules. To avoid confusion, use as few mechanisms as possible and always apply the principle of least privilege. GCP automatically encrypts your data both in storage, known as at rest, and while it's being sent over a network, known as in flight. All API communications use SSL or TLS channels, and every request requires a time-limited authentication token for added security. For data at rest, GCP uses two layers of encryption: data encryption keys and key encryption keys. By default, Google manages these keys, but organizations can choose to manage their own using Cloud Key Management Service, or Cloud KMS, or even supply their own keys for extra control. You can also encrypt your data before uploading it to GCP. This is called client-side encryption. Remember, if you lose your keys, your data is unrecoverable. If your organization handles sensitive data like credit card information, using Cloud KMS helps meet standards such as Payment Card Industry Data Security Standard, or PCI DSS.
Google Cloud Platform meets top security standards like SOC 1, 2, and 3, ISO 27001, and PCI DSS. It also complies with HIPAA, the Cloud Security Alliance Security, Trust and Assurance Registry, or CSA STAR, and the EU-US Privacy Shield framework. Security on Google Cloud is a shared responsibility.
Google secures its infrastructure, but customers must secure their own applications and processes. For example, both Google and customers play roles in network security, especially when protecting against distributed denial of service or DDoS attacks. Google offers features like default anti-spoofing, firewall rules, and Cloud Armor for DDoS defense. Customers should isolate deployments, use load balancing, and restrict public IPs. Google enforces API rate limits and resource quotas to protect all users. If you process credit cards, PCI DSS compliance is essential. Google Cloud holds the highest PCI DSS certification. Isolate your payment environment, use strict firewall rules, and limit access with Identity and Access Management, or IAM. Log all activity and monitor with cloud logging and cloud monitoring. Automate deployments, use configuration management tools, and install intrusion detection systems. Log every action, including admin commands, and export logs to BigQuery for analysis. Rigorous security design on Google Cloud helps protect your organization and customers from damaging incidents. Disaster recovery in cloud architecture is about preparing for the unexpected, from database corruption to hardware failures. Even small incidents can have big impacts, so planning is essential. Two key terms guide disaster recovery. Recovery Point Objective, or RPO, is the maximum acceptable data loss window. Recovery Time Objective, or RTO, is the maximum downtime your application can tolerate. If you use Cloud SQL for MySQL, enable automated backups and point-in-time recovery. This lets you restore your database to a specific moment before corruption. For SQL Server, Cloud SQL supports automated backups, but not point-in-time recovery, so you can only restore to the last backup. Running databases on Compute Engine, you must set up your own backups and transaction logs. Use a service account with the Storage Object Creator role to copy backups to Google Cloud Storage. Custom disk images can speed up recovery and help meet your RTO. For extra resilience, replicate your database to Google Cloud and use monitoring to trigger failover. Hybrid solutions can split traffic between on-premises and cloud using DNS with weighted routing for seamless disaster recovery. Disaster recovery planning is all about balancing cost, complexity, and downtime. The right solution depends on your business needs and risk tolerance. Managing Google Cloud Storage. Managing your cloud storage buckets means more than just setting them up. One of your first tasks is uploading data, and there are several ways to get your files into the cloud. The simplest method is using the Cloud Storage Console. Just click on your bucket, then select Upload Files or Upload Folder. You can even preview certain files directly in your browser after uploading. For those who prefer the command line, the gcloud storage command is handy. To upload a folder called Example Folder from your desktop, use gcloud storage cp-r desktop/example folder gs:// your bucket name. If your internet connection is slow or costly, consider offline import. You can send hard disks or tapes to a provider like Iron Mountain or use Google's Transfer appliance. Transfer your data to the appliance, ship it back, and Google uploads it securely. Need to move data from another cloud provider? Use the Storage Transfer service. Create a transfer job, select your source, destination, and filters, and let Google handle the rest. Transfers can be scheduled to run automatically, daily, or on demand. Default settings prevent accidental overwrites or deletions, making ongoing management simple and reliable. Introduction to Google Cloud SQL. Google Cloud Platform offers powerful tools for storing and processing large amounts of data. One of the most popular options is Cloud SQL, a fully managed relational database service. It is designed to make handling structured data simple and efficient. Cloud SQL organizes your information into tables, rows, and columns. This makes it perfect for storing things like customer lists or product catalogs, and for quickly searching or sorting through your data. You can even join tables to analyze relationships between different sets of information. Cloud SQL is commonly used as a data store for applications running on Google Cloud, such as Compute Engine, Kubernetes Engine, Cloud Run, and Cloud Functions. It can also be accessed by external applications, whether they are on premises or on another cloud provider. Cloud SQL supports MySQL, PostgreSQL, and Microsoft SQL Server. You get industry-standard databases without the hassle of setup or maintenance. Google automates backups, replication, and scaling while keeping your data secure and encrypted at rest and in transit. Cloud SQL is ideal for most relational database needs. For massive scale, Cloud Spanner is more powerful, while BigQuery is built for analytics and big data. Each service is optimized for different tasks, so you can choose the best fit for your project. Introduction to Google Cloud Firestore. Cloud Firestore is a managed, highly scalable, NoSQL document database offered by Google. But what does that really mean? Let's break it down and see how Firestore stands out among other database technologies on the Google Cloud Platform. First, Firestore is fully managed by Google. You do not need to install or configure any software yourself. It is provided as software as a service, so you simply load your data and start writing queries. Google takes care of patches, upgrades, and all the heavy lifting behind the scenes. Firestore is also highly scalable, capable of storing petabytes of data and handling millions of writes per second. This means you never have to worry about capacity planning. As your application grows, Firestore automatically scales to meet your needs. Firestore is a non-relational, or NoSQL database. Unlike relational databases that use rows and columns for structured data, Firestore is ideal for unstructured data like documents or key value pairs. If you prioritize scalability and speed over multi-row transactions, Firestore is a strong choice. Within Google's database offerings, Firestore sits among non-relational databases best suited for building applications, making it a powerful tool for modern development. If you are new to Firestore, Google's cloud database, you might be confused by all the similar names, like Data Store and Firebase. Let's break down Firestore's history and how it fits into Google's ecosystem. Before Firestore, Google offered Data Store, a NoSQL database designed for massive scaling with App Engine. In 2014, Google acquired Firebase, a development platform with its own database. By combining Data Store's scalability with Firebase's advanced storage technology, Google created Cloud Firestore. Firestore operates in two modes: Data Store mode and Native mode. Data Store mode is a compatibility layer, letting developers use the familiar Data Store API while storing data in Firestore's infrastructure. Native mode, on the other hand, uses the new Firestore API, offering features like real-time updates and offline synchronization. Each Google project can only use one mode, so you must choose carefully. If your app needs real-time updates or offline access, native mode is best, especially for mobile and web apps. Data store mode is optimized for server-side processing and does not support these features. Evaluate your project's needs, data model, and pricing to decide which Firestore mode fits best. Firestore's flexibility comes from understanding its history and options. Let's walk through setting up and configuring Firestore. First, log into the Google Cloud Web Console. Search for Firestore and click the link to access the main Firestore page. If it's your first time, you'll need to choose a database mode. You'll see two options, Data Store mode and Native mode. Remember, your choice locks the project to that mode, so review the differences carefully. If your database is empty, you can still switch modes, but once records are added, the selection is permanent. To create a database, click the appropriate button for your chosen mode and select a region. For both modes, you can choose single region for lower latency or multi-region for higher availability and durability. In Data Store mode, records are called entities. Click Create Entity to add one. In Native mode, records are documents inside collections. Click Start Collection to begin. Then add your document with a unique ID. Data Store uses namespaces and kinds to organize entities, while Native mode uses collections and documents. Both can store the same data, just structured differently. Editing and deleting records is intuitive in both modes. Simply select the record, make your changes, or remove it as needed. Indexing helps you search and sort data efficiently. In Data Store mode, choose which fields to index. In Native mode, all fields are indexed by default. For bulk data, Firestore supports importing and exporting records for easier management. To get started with Google Cloud Data Store, remember that you can only import data if it is in a special format. Common formats like comma-separated values, or CSV, are not supported directly. If you need to import a CSV file, you will have to write custom code. Once your data is in Data Store, you can easily build queries in Data Store mode using the console. There is a tab called Query by GQL, where GQL, or Google Query Language, works much like Structured Query Language, or SQL. You can search for entities, filter by author, or look up specific ISBN numbers. Just make sure your fields are indexed, or your queries might return no results. Indexing is crucial for efficient queries. In Data Store mode, you can define composite indexes in your application and review them in the console. In Native mode, you can review single field indexes and create composite indexes as needed. Google can also detect required composite indexes automatically. Now you know how to import, export, and query data in Google Cloud Data Store, as well as manage indexes. Whether you are using Data Store mode or Native mode, these basics will help you get your database up and running smoothly. When developing cloud applications, testing locally is essential. Google provides emulators for Firestore and Data Store, letting you create an isolated development environment. This helps you debug without needing internet access or a dedicated Firestore database. First, make sure you have the Google Cloud Software Development Kit, or SDK, installed. Always run gcloud update to get the latest features and fixes. You will also need a Java runtime installed and configured, since the emulators require Java. Ensure the Java binary is added to your system path. To view available emulators, use the gcloud command to list components. You will see Cloud Data Store Emulator for Data Store mode and Cloud Firestore Emulator for Native mode. Install them with gcloud components install followed by the component name. If needed, also install the SDK beta commands. Start the data store emulator with its specific command. It will run on localhost, usually at port 8081. For Firestore native mode, use its command and it typically runs on port 8040. Check the logs for host and port details. To use the emulators, update your application's environment variables to point to the emulator's address. Your local database will start empty, so refer to documentation for setup details. Now you are ready to build and test locally.
Let's break down Google Cloud Firestore and what makes it so useful. Firestore is a managed, highly scalable, NoSQL document database. If you're building an application that needs to store and retrieve large amounts of unstructured data, Firestore is designed to handle exactly that. Firestore's origins are rooted in the combination of data store and Firebase technologies, which is why the names are so similar. It is important to know that Firestore can operate in two different modes. The first is data store mode, which maintains compatibility with the older data store database. The second is native mode, which introduces new features such as real-time updates and offline synchronization, making it ideal for modern app development. Earlier, we walked through setting up tables, loading data, and writing basic queries in Firestore. We also explored how indexing works to optimize your queries and how to use emulators for local development. These tools make it easier to build, test, and scale your applications efficiently. That wraps up our overview of Google Cloud Firestore. If you have questions or feedback, let us know. And be sure to explore more courses on Tech with Shapingpixel. Introduction to Google Cloud Spanner. Google Cloud Spanner is a fully managed relational database that combines the strengths of both SQL and NoSQL systems. Unlike Cloud SQL, which is ideal for multi-row transactions, or Firestore, which is optimized for speed, Spanner delivers the best of both worlds for demanding applications. With Cloud Spanner, Google handles all maintenance tasks for you. There's no need to install, configure, or update database software. Spanner supports schemas, ACID transactions, and structured query language, or SQL, including both PostgreSQL and Google SQL, which is an ANSI-compliant version. This means you can write queries, manage records, and enforce data access controls with ease. Spanner also offers high availability with synchronous replication across independent zones, achieving up to 99.999% uptime. Cloud Spanner stands out for its horizontal scaling and global reach. You can choose regional or multi-regional configurations, allowing data replication worldwide with low latency. Spanner maintains strong consistency by timestamping every transaction using a global clock, ensuring correct order no matter the region. Developers benefit from open-source emulators, extensive client libraries, and performance tuning tools. If you need a global, scalable, and strongly consistent SQL database, Cloud Spanner is the solution. Getting started with Cloud Spanner is straightforward. First, log in to the web console and search for Spanner. Click the link to access the Cloud Spanner page. If you have not created an instance yet, you will be prompted to do so. Click Create a Provisioned Instance. The form is simple. Pick a name, choose a configuration, and allocate compute capacity. The name is for display, while the instance ID must be unique and can only include letters, numbers, and hyphens. Matching the name and ID helps avoid confusion. Decide between a regional or multi-regional instance. Regional instances offer 99.99% availability and are best if your users are in one area.
Multi-regional instances provide 99.999% availability, higher reliability, and lower latency, but cost more. Choose the region closest to your users for optimal performance. Allocate compute capacity using processing units or nodes. 1,000 processing units equals 1 node. Each node provides about 4 terabytes of storage. Start with enough nodes for your storage needs and monitor CPU utilization to scale as needed. Let us walk through how to create a database and table in Cloud Spanner, Google Cloud's fully managed, scalable, relational database service. This process is straightforward and can be completed in just a few steps. First, scroll down and click on the Create Database button. Choose a name for your database, like demo_db_1. Next, select your database dialect. Google SQL offers more features, but if you prefer Postgres SQL, you can pick that instead. With Google SQL, you can define your schema immediately, including tables and columns. Remember to use underscores, not dashes, in table names. For encryption, most users let Google manage it, but you can provide your own key if needed. Once your selections are set, click Create. To add a table, click on Create Schema or Create Table. Enter your SQL commands in the provided area. For example, create a users table with fields for UUID, name, and email. Set UUID as the primary key using a 36-character string for version 4 UUIDs. This ensures even data distribution and avoids duplicate key errors. After submitting, verify your table by clicking its name. Check that all fields are correct and that UUID is marked as the primary key. Now, your database is ready for applications to read and write records. Managing records in Cloud Spanner is straightforward, especially using the web console. While most applications interact with Cloud Spanner through code, the console offers a hands-on way to add, edit, and query your data directly. First, make sure you have an instance, database, and table set up. Log into the Cloud Spanner console, select your instance, then your database, and finally the table you want to work with. This brings you to the main data management page. To add a record, click Insert and fill in the fields such as UUID, name, and email. Click Run to insert the data. To update, select a record, click Edit, adjust the values, and run the update. For deletions, select the record and click Delete. Each action generates the appropriate SQL command, making it easy even if you are new to SQL. Use the Query option to run SQL statements like select to retrieve specific records. You can also perform more advanced queries, including joins and group bys, for deeper data analysis. Monitoring and insights. Cloud Spanner's console provides dashboards for monitoring CPU utilization, transaction latency, and lock times. Use these insights to optimize performance and troubleshoot issues efficiently. If you are developing an app that needs to store and retrieve data from Cloud Spanner, using the Cloud Spanner emulator is a smart move. It lets you develop offline, saving time and cost. Before you begin, make sure you meet all prerequisites. Installing the Google Cloud Command Line Interface, or G-Cloud, is highly recommended, though not strictly required. Also, the emulator currently requires Docker, so ensure you have the Docker command line tool installed and working. To install the emulator, the easiest way is to use a G-Cloud command that downloads and runs the appropriate Docker container. The first run may take a while, but you will see a message confirming the emulator is running. By default, it listens on port 9010 for Google Remote Procedure Calls, or gRPC, and port 9020 for REST calls. If you did not install the Google CLI, you can use Docker commands directly. Once running, set the Spanner emulator host environment variable so your app connects to the emulator. The client library will look for this variable automatically. Remember, the emulator stores all data in memory, so everything is lost when it shuts down. Use it only for testing and development. For more details, always check the official documentation. Introduction to Google BigQuery. If you want to analyze baby name trends across the United States, Google BigQuery is a powerful tool. To get started, open the Google Cloud Platform console and type BigQuery in the search bar to launch the service. Next, you'll need the right data. Click Add, search for Public, and select Public Datasets. Then, type USA_names to find the baby names dataset. Click on View Dataset to see the available tables. We'll use the first table for our analysis. Clicking on the table reveals its schema and a sample of the data. To start querying, click on Query and choose In New tab. The default query is incomplete, so type Select All to select all data. To find the most popular names, add Order by Number Descending and limit 10. Use the Format Query option for readability. Then click Run. The top result is Robert in New York in 1947 with 10,025 babies. To see only girls' names, add where gender equals F. Now, Mary in Pennsylvania in 1918 tops the list with 8,184 occurrences. BigQuery makes it easy to uncover fascinating trends in baby names. Next, check your query costs before running more analyses. Let's break down how BigQuery pricing works. There are two main components: storage and queries. Understanding these can help you manage your data costs effectively and avoid surprises on your bill. BigQuery's storage charges are impressively low. It costs just 2 cents per gigabyte per month, matching the price of cloud storage standard. If you don't edit a table for 90 days, the price drops to 1 cent per gigabyte per month, similar to nearline storage. Even better, with BigQuery storage, you are not charged for reading data, unlike nearline storage, which charges 1 cent per gigabyte for reads. If you are only using public datasets, you will not see any storage charges at all. The other cost is for queries. The first terabyte of queries each month is free. After that, it is $6.25 per terabyte, or about 2/3 of a cent per gigabyte. Query fees are based on processing, not where your data is stored. So whether your data is in BigQuery storage or cloud storage, the query cost is the same. For steady workloads, capacity-based billing offers predictable query costs, though storage is billed separately. For example, a query processing 163 megabytes would cost less than 1/10 of a cent if you exceed the free tier. To save query results in BigQuery, you first need a dataset. In the menu next to your project name, select Create Dataset and give it a name like baby names. You can also set a location for compliance or an expiration time if you want tables to delete automatically after a certain number of days. Click Create Dataset, and your new dataset will appear under your project. Now, run your query. Before executing, open Query Settings from the More menu and choose Set a Destination Table for Query Results. In the Dataset field, type Baby Names and select it. Enter a table name such as Baby Names Top 10. Click Save, then Run. Your results are now stored in the new table, which you can preview directly in BigQuery. If you forget to set a destination, BigQuery saves results in a temporary table, cached for about a day. Rerunning the same query within 24 hours retrieves cached results, so you are not charged again. However, specifying a destination table bypasses the cache and incurs charges. To clean up, delete the dataset by clicking Delete next to its name. Confirm by typing Delete. This removes the dataset and all its tables. That's how you save and manage query results in BigQuery. BigQuery makes it easy to analyze public datasets, but what about your own data? Let's explore the main ways to load your data into BigQuery, whether it's from Google services or your computer. If your data is in Google Cloud Storage, Google Drive, Firestore, or Bigtable, you can import it directly. For files on your computer, use the BigQuery web interface. Just click Create Table, set the source to Upload, and select your file. BigQuery supports formats like CSV, JSON, Avro, ORC, and Parquet. BigQuery can automatically detect your table schema, but sometimes it guesses wrong. For example, if your file's gender column only has F at first, BigQuery might think it's a Boolean. In these cases, manually specify each field's type to avoid errors. For files larger than 100 megabytes, or if you want to upload many files at once, use the BQ command line tool. It lets you automate uploads and even use wildcards to load multiple files efficiently. You can also stream real-time data using the BigQuery Storage Write API, though streaming incurs a small cost. Remember, you cannot rename datasets, so choose names carefully. Now you're ready to load your own data into BigQuery. Sometimes you need to export data from BigQuery, especially if you want to use third-party tools. The most common method is exporting your data to Google Cloud Storage, then downloading it from there. Let's walk through exporting the baby names table. Click the table name, choose Export to GCS from the Export menu, and specify your cloud storage bucket and file name. You can export in formats like CSV, JSON, Avro, or Parquet. For this example, select JSON. Compression is optional, with gzip as the only choice. Click Save to start the export job. Once finished, check your cloud storage bucket for the file and download it to your computer. If your table is over 1 gigabyte, you must export it in multiple files. For example, exporting the games_wide table in the baseball dataset requires adding a wildcard asterisk in the file name like gamesstar.csv.gz. BigQuery will split the export into numbered files automatically. To avoid ongoing storage charges, delete the exported files from cloud storage. Then return to BigQuery and delete any datasets you created during the process. Exporting from BigQuery is straightforward, but remember to shard large exports and clean up files when finished. Welcome to Loading Data into Google BigQuery. This lesson is designed for data engineers, data analysts, data scientists, and anyone preparing for a Google Cloud certification. By the end of this video, you will understand the essential methods for importing data in BigQuery. You will learn how to import records into BigQuery using several approaches. First, load jobs allow you to upload data directly from files or cloud storage. Next, you can use structured query language, or SQL, to insert data programmatically. The data transfer service automates data movement from external sources into BigQuery, making recurring imports easier. Finally, the Storage Write Application Programming Interface, or API, provides a high-performance way to stream data into your tables. After importing your records, you will discover how to clean up your data using Data Manipulation Language, or DML. DML enables you to update, delete, or insert records, ensuring your datasets remain accurate and organized. Before starting, it helps to be familiar with BigQuery, comfortable with SQL syntax, and have access to a Google Cloud Platform account. Please note, Google frequently updates its products, so minor discrepancies may appear over time. Google BigQuery is a powerful tool for building scalable data warehouses, capable of handling terabytes or even petabytes of information. But importing large volumes of data can be tricky. Let's break down the main methods for getting your data into BigQuery. First, there are load jobs. Think of these as BigQuery's data import wizard. You can add records to a new or existing table from local files or files in cloud storage. Supported file types include Avro, CSV, JSON, ORC, and Parquet. Alternatively, you can use SQL commands, specifically the load data command, to import records from one or more files. The supported file types are the same as with load jobs. Next, the data transfer service is designed for scheduled automatic imports. It can pull data from cloud storage, Google Apps, and even third-party platforms like Amazon Web Services or Microsoft Azure, making it ideal for recurring data transfers. The Storage Write API, part of the Google Cloud Software Development Kit, lets you build custom import tools. It supports both streaming and batch loading, giving you flexibility for real-time or bulk data imports. Finally, other managed services exist outside BigQuery. For example, Dataflow with Apache Beam enables streaming pipelines. DataStream replicates records and schema changes, and the BigQuery connector for SAP allows near real-time SAP data replication. Let us walk through how to import records into BigQuery using a load job, the simplest way to load data into a BigQuery table. We will use the Google Cloud Platform Web Console for this demonstration. First, log into Google Cloud Platform and navigate to BigQuery. Make sure you have a dataset ready, like Import Demo. Click the Add button to start a load job. Select your local CSV file as the source. BigQuery can automatically detect the file type and schema if your file includes column names in the first row. Just confirm your destination dataset and table name, then click Create Table. BigQuery uploads, parses, and inserts your records. For larger files, import directly from Google Cloud Storage. Select your dataset, click Create Table, and choose Cloud Storage as your source. You can specify a single file or use wildcards to select multiple files, such as all files starting with Steam dot and ending with CSV. Again, let BigQuery auto-detect the schema and create your table. After importing, review your table's schema, details, and preview records. Load jobs are great for initial table creation or small batch imports, but they are manual and only support batch mode, not real-time streaming. If you want to import records into BigQuery using SQL, the load data command is your go-to tool. It is perfect for those who prefer SQL over the Google Cloud Platform Web Console for importing external files. To start, you can use the Create Table statement to make a new table or select an existing one. With load data, you specify the dataset and table where your records will go. For example, you might create a table called SQL command inside a dataset named Import Demo. Next, you tell BigQuery which files to import. You can choose from formats like CSV, and you specify the file locations using Uniform Resource Identifiers, or URIs. These URIs can point to files on Google Cloud Storage, Amazon S3, or Azure Blob Storage. And you can even use wildcards to match multiple files. Once you run the command, BigQuery will create the table and import your data. If your CSV file includes column names in the first row, BigQuery will automatically detect the schema and show you a preview of the imported records. Load data is great for batch imports and initial table creation, but it is a manual process. It does not support automation, scheduling, or streaming data imports, so keep that in mind for larger workflows. To import records into BigQuery using the Data Transfer Service, or DTS, you first need an existing table with the correct schema. DTS cannot create tables for you, so start by copying an existing table or defining your schema, then clear any unwanted records. Next, open the Data Transfer Service in BigQuery. If prompted, enable the BigQuery Data Transfer API. Click Create a Transfer, select your data source such as Google Cloud Storage, and give your transfer a descriptive name to help you remember its purpose. Choose your schedule. Run transfers automatically at intervals as short as 15 minutes or select On Demand for manual execution. Specify your destination dataset and table, then select the files to import. Decide whether to append new records or mirror data, which replaces existing rows with the imported ones. You can also set options like deleting source files after transfer or skipping header rows in CSV files. Save your configuration. It will not run until you start it or the schedule triggers. Manage transfers easily. Edit, pause, delete, or run them instantly. DTS is ideal for recurring batch imports to existing tables. Let us explore how to import records into BigQuery using the Storage Write API. While this is not a step-by-step demonstration, we will cover the essential concepts and workflow you need to know. To get started, you will need to write custom code using a Google Client library. Google currently supports C#, Go, Java, Node.js, and Python for the Storage Write API. Once you have imported the appropriate library, you will create streams, which are central to the Storage Write API. Streams allow you to write records to BigQuery, and the process involves calling specific functions to manage your data flow. You can use the default stream for simplicity, calling the append rows function in a loop for each record. For more control, create an application created stream. This involves calling create write stream, then append rows for each record, and finally, finalize write stream to close the stream. The Storage Write API is highly flexible. It supports both batch imports and real-time streaming, handles schema changes, and prevents duplicate streaming records. However, it requires significant coding experience and setup. For complex, continuous imports like telemetry data, the Storage Write API is invaluable. When you import data into BigQuery, it is common to encounter issues like blank fields, incorrect values, or duplicate records. The more records you import, the higher the chance that something needs to be fixed. To clean up your data, BigQuery offers a data manipulation language, or DML. DML is a subset of structured query language, or SQL, but requires you to use Google SQL. If you are using the legacy SQL dialect, you'll need to switch. There are 4 main DML commands: update, delete, insert, and merge. Update lets you fix or reformat records. Delete removes unwanted or duplicate records. Insert adds new records, and merge combines actions for more complex updates. There is also truncate, which removes all rows but keeps the table schema. For large imports, use a staging table. This temporary table holds new records separately, letting you review and fix issues before merging them into your main table. This approach saves time and prevents corrupting your existing data. Limit DML to cleaning and small changes, since BigQuery is not a transactional database. After cleaning, you can share your data securely using Analytics Hub, which helps you organize, advertise, and even monetize your datasets. Data is one of an organization's most valuable assets. So controlling who can view, modify, or delete it in BigQuery is essential. But access control in BigQuery is more nuanced than it first appears. BigQuery uses layers of access control. At the top are basic roles: viewer, editor, and owner, managed through Identity and Access Management, or IAM. These roles apply broadly across Google Cloud Platform services, not just BigQuery. However, basic roles are not very precise, so predefined roles are recommended for more control. Predefined roles in BigQuery can be assigned at the organization, project, dataset, table, or view level. They offer specific permissions like data viewer, data editor, and data owner, and can separate data access from job running permissions. For example, a job user can only start or cancel jobs, while a user can create datasets. To restrict access to certain data, use authorized views. An authorized view lets users see only the results of a query, not the underlying tables, which is useful for sensitive information. For instance, you can let a group see only specific columns by creating a view, granting them data viewer access, and authorizing the view to access the source table. Controlling access to sensitive data in BigQuery is crucial for security and compliance. There are two main approaches: using authorized views to hide sensitive columns, or implementing column-level access control with the Data Catalog service for more complex needs. With column-level access control, you start by creating a taxonomy in the Data Catalog service. A taxonomy is a hierarchical structure that classifies sensitive data. For example, you might have categories like high and medium, with high including credit card numbers and medium including IP addresses. Each specific type of sensitive data becomes a policy tag. Next, you grant access to specific groups based on these policy tags. For instance, you might give the accounting department access to credit card numbers by assigning them the Data Catalog fine-grained reader role on the credit card number policy tag. Access can be granted at broader or more specific levels depending on your needs. Then you tag the relevant columns in your BigQuery tables with the appropriate policy tags. Finally, enable the Enforce Access Control option in your taxonomy. Now, every query checks if the user is authorized to access sensitive columns. While authorized views work for simple cases, column-level access control with Data Catalog is better for managing complex or widespread sensitive data. It centralizes policy management, making it easier to protect data across your organization. Google BigQuery is built for speed and performance, making it one of the fastest data warehousing and analytics platforms available. But to truly unlock its potential, you need to know how to optimize your queries. BigQuery automatically generates indexes to speed up query execution. Its distributed architecture breaks up workloads and runs different parts in parallel, ensuring efficient processing. Additionally, BigQuery stores the results of recent queries in a cache, reducing the need to reprocess data when the same queries are run. Despite these features, your choices in storing and searching data play a major role in performance. The complexity of your queries and the number of columns and rows processed can significantly impact speed. To get the best results, use filtering as much as possible to minimize the data scanned. When using join clauses, select the most efficient join types and avoid expensive operations like cross-join. Be mindful of aggregate functions, such as sum, count, and average, as they can also affect performance. Sometimes, simply changing the order of SQL clauses can make a noticeable difference. Learning these optimization techniques leads to faster execution times, lower costs, and a better experience for your data analysts and engineers. Writing efficient SQL queries in BigQuery is all about reducing unnecessary work. The less data your query reads, processes, and writes, the faster and cheaper it will run. Start by using where, between, and limit clauses. Where clauses help you filter data, but for best performance, use them on columns like bool, int, float, or date instead of string or byte. Between clauses are great for filtering ranges, making your queries more readable and less error-prone. When working with clustered tables, limit can help you test queries without scanning everything. But remember, limit only reduces data read for clustered tables. Avoid using select star, which reads every column. Instead, specify only the columns you need. If you must use a wildcard, try select star except to exclude unnecessary columns. Also, avoid wildcard tables unless absolutely necessary, and always use the most specific prefix possible for better performance. Minimize joins, especially with large tables. Aggregate your data before joining, not after, to reduce the number of rows processed. Finally, break up complex queries into smaller, manageable steps using temporary tables or variables. Follow these strategies to write faster, more efficient SQL queries in BigQuery, making your data analysis smoother and more cost-effective. Boosting BigQuery performance is not just about writing efficient SQL. Leveraging caching can make a huge difference, especially for stable and frequently used queries, delivering faster results and saving on processing costs. Whenever you run a query, BigQuery stores the results in a temporary table for up to 24 hours, unless you specify a destination table. If you repeat the exact same query, BigQuery retrieves results from this cache, providing near instant answers without extra charges. To take full advantage of caching, ensure your repeated queries are identical, including parameters and identifiers. Standardize queries that only differ slightly, as even small changes can turn a cache hit into a miss. Remember, cache results may be invalidated sooner than 24 hours if reference tables or views are modified, so minimize changes and schedule them during off hours when possible. Caching does not work for queries using wildcard tables, external data sources, or non-deterministic functions. Also, very large result sets may require a custom destination table, which incurs storage costs. You can force BigQuery to use only cached results with the require cache flag in the BQ command line tool, or ignore the cache with no use cache. BigQuery's automatic caching is helpful, but sometimes you need more control. That is where materialized views come in. Materialized views let you pre-compute and store the results of complex or frequently used queries, making your data retrieval much faster and more efficient. Imagine you have a dataset called Video Game Example with a table named Scores. This table tracks players' names and their scores from classic arcade games. If you want to create a global leaderboard showing each player's highest score, you can write a select statement to group by player and find their top score. Embedding this query inside a Create Materialized View statement creates a view called Top Scores. This view stores the highest score for each player and updates automatically as new scores are added. Materialized views in BigQuery are always up to date. When the underlying scores table changes, the top scores view refreshes automatically. This means you can share real-time leaderboards or analytics without worrying about stale data. However, materialized views have some limitations. They do not support outer or self-joins, window functions, array subqueries, or non-deterministic functions. Still, they are a powerful tool for efficient, up-to-date data analysis in BigQuery. Lowering your BigQuery costs starts with understanding your pricing options. There are two main models, on-demand and capacity. Choosing the right one for your usage can make a big difference in your monthly bill. On-demand pricing is pay as you go. You are charged for the number of bytes processed by each query, and the first terabyte per month is free. Capacity pricing, on the other hand, is a fixed monthly fee based on reserved slots, or virtual CPUs, letting you run unlimited queries within your slot limit. If you use BigQuery infrequently, on-demand is simple and cost-effective. Use the dry run feature to estimate costs before running queries, and set up maximum bytes build limit to avoid surprise charges. For heavy or predictable workloads, capacity pricing offers better control. Start with a small number of slots and scale up as needed. Consider multi-year commitments for discounts and schedule queries during off-peak hours to maximize idle slots. Regardless of your pricing model, regularly archive or delete unused data to reduce storage costs. Setting up data retention policies can automate this process, ensuring you only pay for what you truly need.
Big data holds valuable insights, but making sense of it can be challenging. That is where data visualization comes in. Visualizations help us spot patterns, trends, and outliers that are hard to see in raw data, making decision-making easier. Looker Studio is Google's business intelligence platform designed for building and sharing dashboards and reports. It connects to hundreds of data sources, allowing you to present information in ways that are both informative and visually engaging. In this lesson, we focus on using BigQuery as a data source. There are two main versions, Looker Studio, which is free, and Looker Studio Pro, which requires a subscription. The Pro version offers enhanced enterprise features and technical support, but most users will find the free version more than sufficient for their needs. Looker Studio is a standalone product, separate from Google Cloud Platform. To access it, visit lookerstudio.google.com. You do not need a Google Cloud Platform account unless you want to use data stored in Google Cloud services like BigQuery. When you log in, you can create new reports or explore interactive tutorials. These tutorials showcase different charts and dashboards. You can use sample data or customize reports with your own data, making Looker Studio a flexible tool for visualizing information.
If you have created a report in Looker Studio and want to share it, there are a few simple ways to do it. Let's walk through your options. First, you can export the underlying data from any chart. Hover over the chart, click the three-dot menu, and select Export. You can save the data as a CSV file, Microsoft Excel file, or Google Sheets. This exports only the data, not the visual chart. To share the full report, click the Share button. Enter email addresses or group aliases to invite viewers or editors. Assign the viewer role for view-only access or the editor role to let others make changes. Advanced options let you restrict editors from inviting others or prevent viewers from downloading or copying the report. You can also share via a link. Choose whether the link is public, unlisted, or limited to your organization. Public links are searchable on Google, while unlisted links are not. Organization-only links restrict access to coworkers. If someone shares a report with you, click the three-dot menu and select Make a Copy. You can use the same data source or switch to a new one.
When you share a report in BigQuery, you are not just sharing the report itself. You're also sharing your connection to the underlying data source, which has important implications. Granting someone editor access means they can view all fields and records in the data source. Any queries they run will be charged to your Google Cloud Platform or GCP account. This makes sharing convenient, but it also means you could be responsible for unexpected costs. You can also share standalone data sources, making it easier to create multiple reports from the same dataset. However, sharing data sources requires caution to avoid exposing sensitive information. By default, reports use the creator's credentials. You can change this so the report uses the viewer's credentials instead. This way, viewers need their own access to the BigQuery dataset, and any charges will be billed to their GCP account, not yours.
This helps protect your account from unwanted costs. Before sharing, always consider who should have access and how much access they need. Sharing can be risky if not managed carefully. Understand exactly what you are sharing and always prioritize data security. Introduction to Google Bigtable. Welcome to your introduction to Google Cloud Bigtable. If you're a data professional or preparing for the Google Professional Data Engineer exam, this overview will help you understand why Bigtable is such a powerful database service. Bigtable is Google's internal database system, designed to deliver real-time access to petabytes of data. It was created to solve the challenge of rebuilding massive web indexes for Google Search, and it's now available as a managed service for everyone. In 2006, Google published a research paper on Bigtable that inspired the creation of other NoSQL databases like HBase and Cassandra. 10 years later, this paper received the SIGOPS Hall of Fame Award for its influence. Today, Bigtable powers core Google services like Gmail and Google Maps. This course covers the best uses for Bigtable, its architecture and storage model, schema design for performance, cluster configuration, access control for security, and running Hadoop jobs that write to Bigtable. You'll also learn about monitoring and pricing. To get hands-on experience, sign up for a Google Cloud free trial, but be careful not to leave Bigtable running too long. Ready to dive in? Let's get started. Google Bigtable is a powerful, scalable database designed for massive applications, like those with billions of users or huge datasets. But it is not the right fit for every project, especially smaller or more traditional applications. Bigtable excels at providing low latency or fast access to large volumes of data. It is best used when you have at least 1 terabyte of data. It stores information as key and value pairs, making it ideal for simple, unstructured data. However, it is not suitable for storing individual data elements larger than 10 megabytes. Bigtable is not a relational database. It does not support SQL or multi-row transactions, so it is not a good choice for online transaction processing or applications needing complex queries. If you need more structure, consider other options. Bigtable shines in big data processing systems, especially with tools like Cloud Data Flow or Cloud Data Proc. It is also a strong choice for real-time analytics, such as financial services or Internet of Things applications, where speed and scalability are crucial. For structured data or SQL support, Google offers Cloud Data Store and Cloud Spanner. Cloud Spanner provides strong consistency and relational features, but at a higher cost. Bigtable is built for massive data. When a client sends a request, it first passes through a front-end server pool, acting as a security layer. The request then reaches a node in a Bigtable cluster, which reads from or writes data to Colossus, Google's file system. Interestingly, nodes in Bigtable do not store data themselves. Instead, they hold pointers to subsets of the table. Bigtable divides tables into groups of rows called tablets. These tablets are stored on Colossus in SSTable format, and each tablet is associated with a specific node. Because nodes only store pointers, Bigtable can easily rebalance workloads. If one node is overloaded, pointers to tablets can be shifted to other nodes. This design allows Bigtable to scale throughput simply by adding more nodes, with no risk of data loss if a node fails. Bigtable's data model is flexible. For example, a stock data table might use the stock symbol as the row key, with columns for last sale, last size, and trade time. Each record is a row, similar to a relational database. When designing a big table schema, your most important decision is the row key. Big table tables are sorted by row key, which is also the only indexed. To avoid slow full table scans, include the most commonly queried fields, like a stock symbol and timestamp, in the row key. Short row keys also improve speed and storage. Columns are grouped into column families, which are stored, accessed, and cached together. If your queries usually retrieve all columns, use a single family, like trade. For more selective queries, group related columns, such as CPU or memory metrics, into separate families to boost efficiency. For time series data, avoid hotspotting by starting the row key with a field, like stock symbol or server name, not the timestamp. This field promotion spreads reads and writes evenly across nodes, preventing any single node from being overloaded. Salting or hashing can distribute data, but they complicate queries. Salting requires multiple scans, while hashing timestamps makes time range queries impossible. Use these only if field promotion is not feasible. Keep row keys under 4 kilobytes, column families under 100, and individual cell values under 10 megabytes for best performance.
When configuring a big table cluster, your choice of storage is crucial. Solid-state drives, or SSDs, deliver impressive performance, up to 10,000 queries per second, 6 millisecond latency for reads and writes, and 220 megabytes per second of scan throughput per node. In contrast, hard disk drives, or HDDs, offer only a fraction of this speed, especially for reads. Big Table scales linearly, so adding more nodes multiplies your performance. For example, 10 nodes can deliver 10 times the throughput of a single node. However, using HDDs to save costs is rarely worthwhile. Although they are cheaper, you would need many more nodes to match SSD performance, which quickly outweighs any savings. To maintain optimal performance, monitor your cluster's workload. If nodes are overloaded, add more through the console or with stack driver monitoring. Remember, performance improvements may take up to 20 minutes under load. Also, development instances have only one node, but you can upgrade them to production for better scalability. Always keep your clients and big table cluster in the same zone to avoid network issues. Choose SSDs unless your workload is massive and not latency sensitive. And remember, switching from HDDs to SSDs later requires migrating all your data to a new instance. Bigtable, Google's scalable NoSQL database, offers access control at 3 levels: project, instance, and table. Understanding how these controls work is essential for managing who can view or modify your data, ensuring both security and flexibility in your cloud environment. There are 3 main roles for controlling access in Bigtable: reader, user, and admin. The reader role allows users to read data in tables and view performance monitoring graphs. The user role grants write access to tables. The admin role provides full access, including the ability to create new instances and manage all aspects of Bigtable. When you assign roles at the project level, permissions apply to every table within that project. For example, a reader can access all data in all tables. If you want more granular control, you can assign roles at the individual table level. However, you cannot restrict access to specific rows or columns within a table. These access controls apply to users with Google Cloud accounts who interact directly with Bigtable. For end users accessing data through your application, you can implement any restrictions you need within your app's logic. To assign roles, visit the Identity and Access Management page in the Google Cloud Console and ensure the Bigtable API is enabled. Cloud Bigtable is Google's powerful NoSQL database, and it integrates seamlessly with Cloud Dataproc, Google's managed service for running Hadoop and Spark jobs.
Today, let's see how they work together. First, enable the necessary APIs: Cloud Pigtable API, Cloud Bigtable Admin API, and Cloud Data Proc API. Next, create a Bigtable cluster. Choose a unique instance ID and select SSD storage for better performance. Then, set up a cloud storage bucket for Dataproc, making sure the name is unique by including your project ID. Use Cloud Shell to clone the example repository and build the Hadoop MapReduce job jar file. Finally, spit up a Dataproc cluster with one master and 4 worker nodes in the same region as your Bigtable cluster. With everything ready, launch the MapReduce job from Cloud Shell. This job counts word occurrences in the Iliad of Homer and stores the results in Bigtable. You can monitor job progress in the Dataproc and Bigtable consoles. Check Bigtable's performance using built-in monitoring tools. Remember, Bigtable pricing is based on nodes, storage, and network usage. For example, a 5-node cluster with 10 terabytes of SSD storage can cost over $4,000 per month.
Google Cloud Bigtable is built for applications that demand low-latency access to massive datasets. It is commonly used for MapReduce operations and real-time analytics. Unlike relational databases, Bigtable is a NoSQL database, so you cannot use SQL to query it. Bigtable's architecture is designed for high performance. Each cluster contains nodes, which point to tablets or groups of rows. Tables are sparse, meaning empty cells do not consume storage, allowing for millions of columns. The row key is the only index, so queries not referencing it require a full table scan. Choosing the right row key is crucial. It should support your most common queries and distribute reads and writes evenly to avoid hotspotting. Group columns often retrieve together into column families. For time series data, use tall tables with fewer columns for efficiency. For optimal performance, use solid-state drives instead of hard disk drives and place client applications in the same zone as your cluster. Assign reader, user, and admin roles in Identity and Access Management, or IAM, at the project level to control access. Monitor your cluster's performance using the web console or stack driver monitoring. You can interact with Bigtable data using the HBase shell or the CBT command. Pricing depends on node count, data storage, and cross-region network traffic. Introduction to Google Cloud Data Flow. Data is the foundation of every modern business. From marketing trends to customer insights and operational performance, companies rely on data to make informed decisions. But with data scattered across different formats and locations, using it effectively can be a real challenge. A data pipeline is an automated workflow designed to move and reformat your data. It copies data from one place, transforms it, and writes the results to another, making your information usable and accessible. Every data pipeline has 3 main phases. First, it reads data from a source, like a database or cloud storage, and stores it in a special container called a P collection. Next, it transforms the data, cleaning, reformatting, or enhancing it. Since P collections are immutable, each transformation creates a new version. Finally, the pipeline writes the transformed data to a destination, such as a data warehouse or cloud storage. Data pipelines break down silos and automate repetitive tasks like extraction, cleaning, and formatting. This ensures your data is always clean, consistent, and ready for analysis.
No more manual exports or endless reformatting. Building and managing data pipelines can be complex and time-consuming. Google Cloud Dataflow is designed to make this process much easier by offering a fully managed, serverless service for executing data pipelines on Google Cloud Platform. With Dataflow, you do not need to manually provision or scale compute resources. The service automatically allocates and scales resources as your workload grows, even during sudden spikes in data volume. Dataflow also takes care of job scheduling, fault tolerance, and monitoring, so you can focus on developing your pipeline logic instead of maintenance. Built-in visualization tools help you quickly identify errors and optimize performance. Dataflow supports both batch and streaming data pipelines using a unified programming model. Batch pipelines process large, finite datasets at scheduled intervals, while streaming pipelines handle unlimited, real-time data, such as live sensor feeds or social media streams. Concepts like windows and triggers help manage and process streaming data efficiently. To build pipelines, you use Apache Beam, an open-source framework supporting Python, Java, and Go. Beam defines your pipeline logic, while Dataflow executes it using distributed processing behind the scenes. For scalable, cost-effective, and simplified data pipelines, Google Cloud Dataflow is a powerful solution.
Every day, companies generate massive amounts of data, measured in petabytes and even exabytes. Managing this flood of information is a challenge, but it also opens up incredible opportunities for innovation and insight. Apache Hadoop, inspired by Google's file system and MapReduce model, was developed in 2006. Hadoop is an open-source framework that enables distributed storage and processing of huge datasets. It works by creating a cluster, which is a group of computers, or nodes, working together as a unified system. Hadoop's core modules include the Hadoop Distributed File System, or HDFS, which breaks files into blocks and spreads them across nodes, and MapReduce, a programming model that processes data in parallel. Yet another resource navigator, or YARN, manages resources and job scheduling, while Hadoop Common provides essential shared libraries. Hadoop clusters are scalable. You can add or remove servers as your data grows. They are also fault-tolerant, storing multiple copies of data across nodes, so failures do not mean data loss or downtime. Hadoop powers data warehousing, log analysis, data mining, machine learning, and financial analysis for many organizations. Despite newer technologies, Hadoop remains a trusted, proven solution for big data challenges worldwide. Hadoop changed the game for big data by making it possible to store and process massive datasets that were previously too large to handle. It quickly became the foundation of the big data ecosystem, with many tools built around it. However, Hadoop's MapReduce model relies heavily on reading and writing files to disk, making it slow for many tasks. This led to the development of Apache Spark, a faster and more versatile open-source analytics engine designed for large-scale data processing on clusters. Spark stands out because it performs computations in memory, making certain tasks up to 100 times faster than Hadoop. Its high-level APIs and interactive shells also make Spark easier to learn and use, especially for data scientists and analysts. Spark Core handles storage, scheduling, and memory management. Spark SQL lets you use SQL queries on structured data. Spark Streaming processes real-time data in microbatches. MLlib provides machine learning tools, and GraphX enables graph processing and analysis. Hadoop is best for offline batch processing, while Spark excels at real-time analytics, interactive queries, and fast machine learning. You can even combine both,
storing data on Hadoop's file system, and running queries with Spark for maximum flexibility. Google Cloud Platform offers a range of big data solutions, whether you're building from scratch or migrating existing workloads. But how do you choose the right tool for your needs? Manually setting up Hadoop or Spark clusters on virtual machines can be complex and costly. You need to provision servers, configure networks, install software, and handle ongoing maintenance. Plus, you often pay for resources even when they are idle, making clusters inflexible and expensive. That is where Google Cloud Dataproc comes in. Dataproc is a managed service for running Hadoop and Spark jobs on Google Cloud Platform. It eliminates the hassle of manual setup, letting you spin up clusters in minutes and scale them easily as your needs change. With Dataproc, you only pay for what you use, with no upfront costs or overprovisioning. It is fully integrated with other Google Cloud services like Cloud Storage, BigQuery, and Vertex AI, making data import, storage, and machine learning seamless. Dataproc offers auto-scaling, workflow templates for reusable pipelines, and even Dataproc Serverless, which runs Spark jobs without managing clusters. Focus on your data, not your infrastructure, with Google Cloud Dataproc. Database planning on GCT. Building a production database is a critical task. Every part of your system will rely on it, so any mistakes can have far-reaching consequences. If your database is slow or goes offline, your entire application will feel the impact. Switching databases later is rarely simple. It can be time-consuming, expensive, and sometimes impossible if your system depends on unique features. That is why choosing the right database from the start is a long-term commitment you need to get right the first time. The pressure to make the right choice can feel overwhelming. You need to understand your options and keep your system as flexible as possible. Fortunately, Google Cloud offers a wide range of database types and features to help you find the best fit for your needs. Choosing the right database on Google Cloud Platform starts with understanding your needs. There is no one-size-fits-all solution. Each database is optimized for different workloads, so knowing your requirements is key. First, ask yourself, who will handle setup and maintenance? Managed databases let Google handle provisioning, configuration, licensing, and updates. You simply pick what you need and Google does the rest. If you need deep customization, consider unmanaged databases. Here, you are responsible for everything, from infrastructure to security patches. Next, decide between relational and non-relational databases. Relational or SQL databases like MySQL and Postgres are great for structured data and complex queries. Non-relational or NoSQL databases like MongoDB and Cassandra excel at handling unstructured data and scaling quickly. Google offers 6 main managed databases. For relational needs, choose Cloud SQL, Cloud Spanner, or BigQuery. For non-relational, consider Firestore, Bigtable, or Memory Store. Each is tailored for specific scenarios, from mobile apps to massive analytics. If you need something unique, like Oracle, explore bare metal solution or partner services. These options support specialized workloads and custom solutions. Understand your data and use case, and you will find the right Google Cloud database for your project. Capacity planning is essential for any database project. It means figuring out how much load your database needs to handle, including users, simultaneous connections, disk space, and operations per second. Getting this right ensures your system runs smoothly. If your system is too small, you risk slow queries, data corruption, or even crashes. But if it is too large, you are wasting money. The goal is to balance price and performance by understanding your workload and planning accordingly. For unmanaged databases, review documentation for hardware requirements and use current usage data as a reference. For managed solutions like Cloud SQL or Cloud Spanner, select machine types, storage, and processing units based on your needs. For serverless options like BigQuery and Firestore, Google handles scaling automatically. Consider shadow deployments to test workloads without affecting production. Use synthetic benchmarking tools like HammerDB for new projects. Always monitor performance and set up alerts to catch issues early. Google's Cloud Monitoring API can help track key metrics and enforce policies. Finally, always check service quotas. Even if your database can handle high loads, you may need to request a quota increase to match your expected usage. Careful planning now prevents headaches later. Database capacity planning is all about making your best estimate and being ready to adjust. Workloads can be unpredictable, and as your service grows, so will your database needs. So, how do you scale effectively? There are two main approaches: vertical scaling and horizontal scaling. Vertical scaling means upgrading your existing machine's resources, like adding more CPUs or memory. But this has limits and usually requires downtime. Horizontal scaling, on the other hand, means adding more machines or instances. This can help avoid downtime and lets you scale as much as your budget allows, but not all databases support it. With Google Cloud SQL, you can vertically scale by upgrading your instance or create read-only replicas for horizontal scaling, but only reads benefit. Cloud Spanner lets you add nodes for vertical scaling without downtime, or use tools like Autoscaler for automatic adjustments. BigQuery and Firestore handle scaling automatically. Bigtable allows manual or automatic node adjustments, but autoscaling works best for predictable growth. Memory Store supports vertical scaling, but expect brief downtime during changes. Ultimately, choose your scaling strategy based on your workload patterns and database features. Be prepared to monitor, adjust, and plan for both growth and unexpected spikes. No matter how well you design your database system, some downtime is inevitable. Whether it is a hardware failure, a network issue, or just routine maintenance, you need to be prepared. Every database should have a disaster recovery plan. The right plan depends on your data and business needs. Ask yourself, does your database require zero downtime, near zero downtime, or can you tolerate occasional outages? Your answer will guide whether you need manual recovery or automated solutions. For production systems, high availability is crucial. This means your data remains accessible even if part of the system fails. The key is redundancy, running multiple instances so if one fails, others take over. Distributing these instances geographically can protect against larger failures, like losing an entire zone or region. Google managed databases make redundancy easier. Cloud SQL can be configured for multiple zones or regions. Cloud Spanner and BigQuery default to multi-zone setups, with options for regional or multi-regional configurations. Memory Store's standard tier adds replicas for automatic failover, while Bigtable allows extra clusters in other regions. Before building, evaluate your needs and costs. Not every database needs high availability, but planning ahead ensures your data stays safe and accessible. Google Cloud offers a wide range of database options, but more features often mean higher costs. Let's quickly see how to estimate your database expenses and discover ways to save money. Start by visiting cloud.google.com/products/calculator. Select the database product you want, like Compute Engine for custom setups. Fill in details such as machine type, number of instances, storage type, and region. For example, choosing a memory-optimized machine and setting a 500-gigabyte boot disk. Always select the correct region as prices can vary significantly. The calculator lets you compare different configurations. Try adding a 3-year committed use discount to see potential savings. For instance, switching to a 3-year commitment can show a $9,000 per month difference. For managed services like Cloud SQL, search for the product, pick your instance type, storage, and backup needs. Enable high availability only if necessary, and consider committed use discounts for additional savings. Monitor usage with cloud monitoring, scale automatically with tools like Autoscaler, and choose the right storage type. Optimize queries, review regional pricing, and only enable high availability when needed. These steps help keep your Google Cloud database costs under control.
Let's quickly review the key concepts you've learned so you can confidently apply them to your business or technical projects. This summary will help reinforce your understanding. First, selecting the best database starts with 3 essential questions. Who will manage and maintain your database? What type of data will you store? And how will it be used? Are there any special requirements or edge cases? Your answers will guide you toward managed or unmanaged solutions, relational or non-relational databases, and even specialized options like bare metal or partner services. Next, we discussed capacity planning. It's crucial to provision the right amount of resources. Too little, and your database can't keep up. Too much, and you waste money. Use monitoring and alerts to ensure your configuration meets your needs, and to know when upgrades are necessary. Scaling your database can be manual or automatic. Vertical scaling means upgrading existing instances, while horizontal scaling involves adding new ones. Both approaches help your database handle increased demand efficiently. To avoid downtime, create failover replicas and distribute them across multiple zones or regions. This makes your database resilient and ensures continuous availability. Finally, estimate costs using the pricing calculator tool and optimize your spending. Database migration strategies for GCP. Migrating a production database to Google Cloud can seem overwhelming, but breaking it down into clear steps makes the process manageable. Let's explore the essential phases and best practices for a smooth migration. Start with the assess phase. Document every component of your current system, including all applications, servers, and resources. Identify both dependents, which rely on your database, and dependencies, which your database relies on. List out performance requirements, current costs, and any special needs like encryption or compliance. Understanding your system structure and requirements is crucial before making any changes. Next, select the right database technology for Google Cloud. Consider features, scalability, maintenance, and pricing. If multiple options fit, prototype with sample data to test your use cases. Remember, copying a MySQL instance differs from migrating Postgres to Cloud Spanner, so choose carefully. For smaller or less dynamic databases, a simple export and import may work. For larger or constantly updated databases, use tools like Database Migration Service or Cloud Storage. If your data is massive, Google Transfer Appliance can help speed up the process. Document everything, share with your team, and choose tools that fit your needs. With careful planning, Google Cloud offers solutions for every migration scenario. The second phase of database migration is all about planning. Start by mapping out your final solution in detail, including every step and the end state. Use your list of dependencies to determine what needs to change and in what order. Building prototypes or proof of concepts can be invaluable. If you are unsure where to begin, try migrating a test database and document each step. This helps you compare options and estimate realistic timelines and costs for your migration.
Decide whether you need a one-time migration or a continuous migration. One-time migrations are simpler and involve taking the database offline, while continuous migrations keep the database online and synchronize data over time, minimizing downtime. For one-time migrations, consider breaking the process into stages or using incremental backups to reduce downtime. Continuous migrations are best for large, frequently updated databases or when downtime is not an option. Every migration plan needs a clear methodology and a fallback plan. Prepare for failures by planning how to revert changes if needed. Automate as much as possible to reduce risk and ensure both migration and rollback steps are reliable. The third migration phase is all about deployment. This is where you set up your infrastructure, provision your database, and move your data. It is the moment when your planning turns into real, working systems. Automation can make this process smoother. Google Cloud offers tools like the Google Cloud Software Development Kit, or SDK, for custom scripts, and you can use Terraform or Kubernetes templates to provision resources. Schema conversion is often tricky, so tools like Dataflow, Cloud Data Fusion, and Cloud Composer can help reduce risk. A typical migration involves copying your records, testing everything, migrating client connections, and then retiring your old database. If you are doing a live migration, you will need to drain client connections by pausing updates and letting the new database catch up. Always take a backup before switching clients to the new environment. After migration, thorough testing is crucial. Unit, integration, and regression tests ensure everything works. Use cloud logging and monitoring to track performance and set alerts for issues like CPU usage exceeding 75%. Having enough resources and people on hand is vital for handling last-minute issues. If you planned well in earlier phases, this step should be smooth execution. After completing your migration, the next crucial step is optimization. Start by gaining a clear understanding of your system's health. Track how often error messages occur, what types they are, and the speed of your queries. Effective diagnostics are essential, so build tools that make troubleshooting quick and easy. It is not enough to simply collect logs. You need a powerful way to search through them. Use Cloud Logging and Logs Explorer to stay on top of issues. Go beyond reacting to problems by setting up cloud monitoring to send alerts for spikes in demand or slow queries. Once you can measure and monitor everything, look for improvement opportunities. This might mean rewriting queries, generating missing indexes, or converting transactions to minimized locking. If you have a large monolithic database serving multiple microservices, consider breaking it up for easier maintenance and better data storage formats. Review your options for availability and scalability. Google Cloud helps you handle spikes in demand and outages. Small changes can lower your monthly bill. Switching to Google Managed Services can reduce administrative and licensing costs while improving scalability. Managed instances integrate seamlessly with Google's ecosystem, making advanced analytics and machine learning more accessible for your data. Let's quickly review the 4 essential phases of database migration so you can approach your next project with confidence and clarity. The first phase is assess. Here you identify all dependents and dependencies. That means everything that relies on your database and everything your database relies on. Once you have a clear picture, you can select your target database and choose the right tools and automation to support your migration. Next is the plan phase. In this stage, you decide on your migration methodology and write out every required step. It's also crucial to develop a fallback plan. Start by asking yourself if this migration will be a one-time event or a continuous process, as this will shape your approach. Now it's time to deploy. This is where you put your plans into action by creating your new database instance, replicating records, and migrating client connections. Careful execution here ensures a smooth transition. Finally, optimize. Make sure logging and monitoring are set up to catch issues early. Look for ways to boost performance, resilience, and cost efficiency. Thanks for watching, and don't forget to rate the course. Setting up a production database on Google Cloud Platform is just the beginning. The real challenge is keeping it healthy over time. That is where monitoring and quick issue detection come in. Google Cloud offers a tool called Cloud Monitoring. Cloud Monitoring lets you track your cloud resources performance using dashboards and alerts. This way, you can spot problems before they impact your database. After logging into the Google Web Console and searching for monitoring, you will find dashboards. These dashboards display charts and graphs showing metrics like queries, page reads, network connections, and CPU utilization for your Cloud SQL database. While Google provides default dashboards, you can create your own. Simply click Create Dashboard, then drag and drop charts for the metrics you care about, such as CPU utilization or connection counts. Customize them to fit your needs and save your dashboard for future use. Instead of watching dashboards all day, set up alert policies. Choose a metric like CPU utilization, set a threshold, and pick how you want to be notified: email, SMS, Slack, or more.
Monitoring and alerting are built in for all Google managed services like Cloud SQL and Firestore. But what if you are running an unmanaged service, such as MySQL on a compute engine virtual machine? In that case, you can install the Ops Agent. The Ops Agent collects telemetry data from your virtual machines and sends it to Cloud Monitoring. The easiest way to install it is through the web console. Just click Set up Agents, select your virtual machines, and hit Install or Update Agents. Google handles the rest, and soon your metrics will appear in Cloud Monitoring. Prefer manual installation? You can copy the provided commands for Linux or Windows and run them in your terminal or include them in a custom startup script. This flexibility lets you monitor any database, even if it is not managed by Google. But what should you monitor? Focus on service level indicators, or SLIs, which measure your service's performance. Set service level objectives, or SLOs, as internal goals and service level agreements, or SLAs, as customer commitments. Identify your key metrics, set up dashboards, and create alert policies to stay informed and maintain reliable service. When a database problem strikes, finding the root cause quickly is crucial. That is where log files come in, capturing everything from debug info to critical errors. But with massive, scattered logs, searching can be overwhelming. Google's cloud logging service centralizes all your logs, making them easy to manage. If you use a Google-managed database, just enable logging. For custom solutions, install and configure the Ops Agent. Once set up, your logs flow into cloud logging automatically. To view them, log into the Google Web Console and search for Logs Explorer. Logs Explorer displays all your log entries and lets you filter by time, resource type, severity, and more. For example, you can narrow results to Cloud SQL warnings from the last 12 hours. Use the filter options or write your own filter expressions. The search feature highlights keywords like fail or insecure, helping you pinpoint issues fast. Click any entry to expand details, formatted in JSON. Need to analyze logs elsewhere? Use the Create Sync option to export filtered logs to cloud storage, BigQuery, or Splunk. Just name your sync, set filters, and choose your destination. With cloud logging and Logs Explorer, tracking down database issues becomes faster and more manageable. Use filters, search, and export tools to find exactly what you need. Google Cloud Platform, or GCP, enforces quotas to limit how you use their services. For example, Cloud Firestore allows only 200 composite indexes per database. Knowing these limits is crucial for smooth operations. To check your quotas, log in to the GCP Web Console and search for IAM. Scroll down the left menu to find Quotas. Here, you will see all your quotas, often with multiple limits per product. Use the filter to narrow down to the service you are interested in, like BigQuery. For instance, BigQuery has a quota of 3,000 IAM policy requests per minute. Exceeding this will result in errors. If you need a higher quota, select the relevant entry and click Edit Quotas. Enter your new maximum, provide a compelling justification, and include your contact information. Google will review your request and may approve or deny it, so be clear about your needs. Set up monitoring by clicking the Show Usage Chart icon to compare your usage to the maximum. You can also create quota alerts, which notify you when you approach a limit, and customize notification channels. Always review quotas for your services, set up alerts, and request increases when necessary to avoid disruptions.
Introduction to Google Cloud PubSub.
Google Cloud PubSub is a scalable message queuing service designed for communication between different applications or services. Unlike email or chat, it is built to track changes and share updates across various systems, making it ideal for modern cloud architectures. Instead of sending messages directly from one application to another, PubSub stores updates posted by applications. Later, other applications can retrieve these updates whenever they need. Think of it less like sending an email and more like posting on a blog or forum, where messages are published and anyone interested can read them later. Cloud PubSub supports multiple communication patterns. It can handle one-to-many, many-to-one, many-to-many, or even one-to-one messaging. This flexibility means senders do not need to track recipients, and recipients only receive messages they care about. Cloud PubSub is highly scalable, capable of handling massive amounts of data. Google uses it in products like Ads, Search, and Gmail to send over 5 million messages per second, totaling more than 1 terabyte of data. In short, Google Cloud PubSub enables scalable, reliable, asynchronous messaging between applications, making it essential for communicating change events in cloud-based systems. Cloud PubSub is a messaging service that connects applications using the publisher and subscriber model. It lets you send, receive, and process messages between independent systems, making communication flexible and scalable. A message is simply data exchanged between services. It can be a simple text, a number, or a complex object like JSON. Messages are grouped into topics, which act as queues for related messages. Each topic represents a specific category, such as new user registrations. A publisher is any service that adds messages to a topic. Multiple publishers can send messages to the same topic. Subscribers are services that want to receive messages from topics. Each subscriber needs a subscription to a topic to start receiving messages. Subscriptions link subscribers to topics. Each subscription delivers one copy of a message to one subscriber. If you want every subscriber to get every message, each must have its own subscription. Messages published before a subscription is created are not delivered to that subscription.
Subscribers can pull messages manually or have messages pushed automatically to an endpoint. Pull subscriptions offer control, while push subscriptions deliver messages instantly as they arrive. Subscribers must acknowledge each message. Unacknowledged messages are resent, ensuring reliable delivery even if a subscriber temporarily fails. This makes Cloud Pub Sub resilient and dependable. Cloud Pub Sub offers two main services, Pub Sub and Pub Sub Lite. Both are message queuing solutions, but they serve different needs and budgets. Let us break down what sets them apart so you can make an informed choice. Pub Sub is the more robust option, providing high reliability, per-message parallelism, global routing, and automatic capacity scaling. It replicates messages across multiple zones and features unlimited storage, though messages are retained for up to 7 days. With PubSub, you only pay for what you use. On the other hand, PubSub Lite is designed for affordability. It is limited to a single zone, requires manual capacity management, and offers a little over 10 terabytes of storage per topic. While it allows for unlimited message retention, you pay for what you provision, which means unused capacity can lead to unnecessary costs. PubSub Lite also has lower availability and durability. For most users, PubSub should be the default choice due to its reliability and flexibility. However, if cost is your primary concern and your workload can tolerate lower availability, PubSub Lite may be a better fit. Always consider your specific requirements before deciding. Cloud PubSub is a powerful tool with a wide range of applications. Today, let's explore some of the most common use cases that highlight its versatility in modern cloud environments. One major use for Cloud PubSub is real-time event processing. It enables organizations to create an enterprise-wide data sharing bus, allowing business events, user interactions, and even system failures to be tracked and responded to as they happen. This real-time capability is essential for businesses that need immediate insights and actions. Google Cloud PubSub is a scalable message queuing service designed for reliable, asynchronous messaging between different applications and services. It is highly flexible, supporting one-to-many, many-to-one, and many-to-many communication patterns, making it a powerful tool for connecting distributed systems. PubSub operates using messages, topics, publishers, and subscribers. Messages contain the data to be sent, often about a change event. Topics act as categories for these messages, storing them and controlling what types are received. Publishers are applications that add messages to a topic, while subscribers are applications that read messages from a topic. Each subscriber needs a subscription per topic, and subscriptions can be shared or individual. Shared subscriptions send each message to one subscriber at random. Subscriptions can be pull, where subscribers manually check for new messages, or push, where the topic notifies subscribers automatically. There are two services, PubSub and PubSub Lite. PubSub offers higher reliability, more integrations, and automatic provisioning, but at a higher cost. PubSub Lite is less expensive but requires more operational work and offers lower availability. For most scenarios, PubSub is recommended. That wraps up our overview of Google Cloud PubSub. If you have questions or feedback, let us know, and be sure to explore more of our courses. Cloud PubSub lets you subscribe to topics and receive messages, but sometimes you only want a specific subset. That is where custom subscription filters come in, helping you focus on just the messages you care about. Imagine you have a topic called New User Accounts that notifies you about all registrations. If you only want to process premium user signups, filtering is much more efficient than handling every single message and discarding most. Filters use message attributes, which are key value pairs containing metadata. You cannot filter based on the message content itself, only on these attributes. For example, you might add an attribute called type with values like free or premium. To filter for premium users, you would create a subscription with the filter expression such as attributes.type equals premium. Filters are set at the subscription level, so each subscription can have its own unique filter without affecting the topic or other subscriptions. For instance, if you want only English messages, set an attribute language to EN-US and filter with attributes.language equals EN-US. Only messages matching this filter will be delivered to your subscription.
Cloud Pub Sub can process millions of messages every second, but sometimes messages arrive out of order. For many use cases, this is fine. However, when order matters, enforcing message ordering becomes critical. To guarantee message ordering, you need two things: add an ordering key to your messages and enable message ordering in your subscription. Both steps are required. Ordering keys do not represent sequence numbers. Instead, they group related messages so that only those with the same key are delivered in order. Imagine sending 4 messages, 1 and 2 with the ordering key alpha, and 3 and 4 with beta. You are guaranteed to receive 1 before 2 and 3 before 4, but not necessarily 2 before 3. If all messages share the same key, their order is preserved. Enabling message ordering can increase latency and may result in duplicate messages. When a message with an ordering key is redelivered, all subsequent messages with that key are also redelivered. Only enforce ordering when absolutely necessary. Create a topic, then a subscription with message ordering enabled. Send messages with ordering keys to guarantee their order. Acknowledge each message to receive the next in sequence. When using Cloud Pub Sub, sometimes messages cannot be delivered to a subscriber, even after multiple attempts. To prevent losing these undeliverable messages, you can set up a dead letter topic. First, create your main topic to hold original messages. For example, name it Topic 3. Next, create a dead letter topic, just like any other topic, but with a name that makes its purpose clear, such as Topic 3-Lost. Now, create a subscription for your main topic. For instance, call it Subscription 3 and make sure it subscribes to Topic 3, not the dead letter topic. Scroll down in the subscription settings and enable dead lettering. Select your dead letter topic, like Topic 3-Lost, and set the maximum number of delivery attempts, such as 10. After this number, undeliverable messages will be moved. Grant the necessary permissions, allowing publishing to the dead letter topic and reading from the main topic. This ensures messages can be transferred properly. Finally, create a subscription for your dead letter topic. For example, Subscription 3-Lost, so no messages are lost. That's how you set up a dead letter topic. In Cloud Pub Sub, you can format your message data however you like, as long as it can be encoded into a string. But this flexibility can cause issues if subscribers expect a specific format, like a JSON object, and receive something else instead. A message schema solves this by creating an enforced contract between publishers and subscribers. Everyone knows exactly what format the message data must follow. For example, if your schema defines a JSON object, you cannot publish just a plain string. To use a schema, you must create it first, then create a topic that uses it. You cannot add a schema to an existing topic, so plan ahead. Schemas can be defined using Apache Avro, which uses JSON, or Protocol Buffer, Google's method for serializing structured data. Once your schema is ready, create a topic and select Use a Schema. Pick your schema and set the format to JSON. Now, any message published to this topic must match the schema. If it does not, publishing will fail with an error.
This approach ensures all subscribers receive messages in the expected format, making it easier for teams to collaborate and share topics. By reusing schemas across topics, you can even enforce company-wide standards for message formats.
Cloud PubSub is designed to deliver each message once, but sometimes duplicates slip through. Handling these duplicate messages is important to keep your systems running smoothly and your data accurate. To reduce duplicate messages, start by extending the message deadline. Duplicates often happen when a subscriber takes too long to acknowledge a message. Giving subscribers more time can help. If your subscribers are overwhelmed, consider adding more or upgrading their capacity. Also, enforcing message ordering can increase duplicates. If strict ordering is not necessary, try disabling it to see if duplication decreases. While these steps can lower the number of duplicates, they will not eliminate them completely. Filtering out duplicates on the subscriber side is usually straightforward. Add logic to check if a message has already been processed. For example, if you are encoding videos, check if the video is already encoded before starting. Every message in a topic has a unique message ID. Store these IDs in a database or cache to track processed messages and compare suspected duplicates. If you cannot tolerate any duplicates, use the Apache Beam programming model. Apache Beam with Cloud Data Flow and the Beam PubSub I/O connector can filter out all duplicates for you. Cloud PubSub guarantees at least once delivery. For exactly once delivery, you'll need extra logic or tools.
Normally, once you acknowledge a message in your subscription, it is gone for good. But what if a bug causes you to acknowledge messages by mistake? Fortunately, message recovery is possible using the Seek feature, which lets you replay or purge messages as needed. The first method is called Seek to Timestamp. Here, you pick a specific time, and all messages sent before that time are marked as acknowledged, while those sent after are unacknowledged. This is a quick way to recover messages lost in a recent incident, or to prevent bad messages from being delivered. However, you must enable the Retain Acknowledged Messages option for your subscription, which can increase costs. Also, you cannot recover messages older than the retention period, usually 7 days, and the operation affects all messages in bulk. The second method is Seek to Snapshot. Snapshots capture the acknowledgement state of messages at a specific time, without storing the actual message data. You can restore this state later, as long as the messages still exist. Snapshots do not require retaining acknowledged messages, making them a more cost-effective option. Both Seek methods offer powerful tools for message recovery and debugging. Choose Seek to Timestamp for quick, broad changes, or Seek to Snapshot for more control and lower costs. Monitoring Cloud PubSub becomes essential as your system grows more complex with multiple topics and subscriptions. Identifying and diagnosing issues early helps keep your messaging infrastructure reliable and efficient. Cloud PubSub automatically exports its metrics to cloud monitoring, giving you ready-to-use default dashboards. These dashboards display general information about your topics, such as operations and average message size. You can also drill down for details on specific topics and their associated subscriptions. Beyond the defaults, you can create custom dashboards to track specific metrics that matter to your workflow. More importantly, setting up alerts ensures you are notified if something goes wrong. For example, you can create an alert for unacknowledged messages by setting a threshold, like 500, and choosing how you want to be notified, such as by email. Monitor metrics like oldest snapshot message age, unacknowledged messages, and acknowledged message operations. Filtering by response codes helps identify issues with pull or push subscriptions. For topics, track publish operations and group by response code to ensure PubSub is healthy and messages are flowing. Check your PubSub quotas under IAM and admin to avoid hitting API limits. Filter by cloud PubSub and region to see your usage and set custom alerts if needed. Proper monitoring lets you detect and resolve issues before they impact your users, making it a crucial part of any production cloud PubSub setup. Introduction to Machine Learning on GCP. You have probably heard the buzzwords artificial intelligence, machine learning, and deep learning. But what do they actually mean? And how are they connected? Let's break down these terms in simple language. Artificial intelligence, or AI, is a branch of computer science aiming to create intelligent, thinking machines. Think of characters like C-3PO from Star Wars or Commander Data from Star Trek. The goal is to build machines that can solve complex problems on their own, just like humans. Machine learning, often called ML, is a subset of artificial intelligence. Instead of aiming for full human-like intelligence, machine learning focuses on creating algorithms that can learn and improve by themselves. It is a practical step toward the bigger dream of AI. One way to achieve machine learning is through neural networks, which mimic the human brain using interconnected nodes. Deep learning is a special type of neural network with multiple hidden layers, allowing machines to tackle even more complex problems. So, AI is the broad goal, machine learning is a step toward that goal, neural networks are one way to do machine learning, and deep learning is the most advanced form of neural networks. Now you know the difference. Machine learning is all about recognizing patterns in data to solve problems, but it is not magic. There are 4 main approaches: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Each has its own strengths and ideal use cases. Supervised learning is like learning by example. Imagine a child learning to tell dogs from cats by seeing labeled pictures. In machine learning, algorithms are trained on labeled data, then tested on new data to see if they can correctly identify patterns. This approach is perfect for classification, like sorting emails as spam or not, and regression, such as predicting tomorrow's temperature. Unsupervised learning does not need labeled data. Instead, it finds patterns on its own, grouping similar items together. Think of it as discovering your favorite foods without anyone telling you what to like. It is great for clustering, like grouping customers by behavior, and association, such as recommending products based on past purchases. Semi-supervised learning combines both labeled and unlabeled data, offering guidance when full labeling is not possible. Reinforcement learning teaches algorithms through trial and error, helping them make decisions like finding the best travel route. Machine learning automates simple tasks and tackles complex problems, but it still has limits. Its power lies in finding patterns humans might miss, making it a valuable tool in today's world. Machine learning works by recognizing patterns in data. You start by feeding lots of information into a computer, which then uses mathematical or statistical techniques to find patterns. These patterns are stored in what is called a model, which can then be used to make decisions or classify new data. To create a model, you need two things: a dataset and an algorithm. The dataset could be anything from numbers to photos or music. The algorithm, often based on statistics or calculus, processes the data and builds the model. Once trained, you can give the model new data and it will predict or classify based on what it has learned. The inputs you give to a model are called features. For example, a model predicting car prices might use features like age, mileage, and brand. The output is called a label, such as the predicted price. More features can help the model make better predictions. Models are not perfect. They make predictions, not guarantees. To measure how well a model works, we use evaluation metrics like accuracy, precision, and recall. These metrics help us understand and improve the model's performance. Over time, models can become less accurate as trends change. That is why retraining with new data is important. In summary, machine learning is about finding patterns, building models, and constantly improving them with fresh information. Machine learning is a fascinating field that sits within artificial intelligence, or AI. While AI aims to create machines with human-like intelligence, machine learning focuses on building systems that can learn and improve from experience. Deep learning, a subset of machine learning, uses complex neural networks inspired by the human brain to solve even more challenging problems. Throughout this introduction, you explored the differences between artificial intelligence, machine learning, and deep learning. Artificial intelligence is the broadest category, while machine learning is a specialized area focused on learning from data. Deep learning takes things further by using multi-layered neural networks to process information in ways similar to how our brains work. Machine learning tackles a variety of problems using four main approaches: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Supervised learning uses labeled data and tests to solve classification and regression problems. Unsupervised learning works with unlabeled data to find patterns. Semi-supervised learning blends both methods. Reinforcement learning relies on trial and error to find the best solutions. You feed data into an algorithm to create a model. With this model, you can input features and receive predictions or labels as outputs. Thanks for watching, and be sure to explore more courses. If you are interested in machine learning, you will want to know about Vertex AI. Vertex AI is Google's new managed machine learning platform, designs that help you build, deploy, and maintain your own machine learning models from start to finish. Vertex AI is a platform made up of many different products. There are tools for managing and labeling datasets, training models, conducting experiments, and deploying your models. Think of it like Microsoft Office, which includes Word, Excel, and PowerPoint. Vertex AI replaces Google's older AI platform, but both currently exist, so there is a transition period for users. Most people start by uploading and labeling data. You can train models using AutoML, which is a managed service that lets non-experts create models without code, or use custom training if you want to write your own code. Once your model is ready, Vertex AI helps you evaluate, store, and deploy it for real-time or batch predictions. Vertex AI also supports Jupyter Notebooks, experiment tracking, and tools for logging, monitoring, and managing metadata. It heavily promotes MLOps, or machine learning operations, to streamline deployment and minimize risks. Vertex AI offers a comprehensive suite of tools for machine learning on Google Cloud Platform, making it easier and more efficient to manage the entire machine learning lifecycle. Welcome to this introduction to Google Vertex AI Workbench, designed for machine learning engineers and anyone preparing for a Google Cloud certification. Before we begin, make sure you have access to a Google Cloud Platform account, or GCP account, as this is a key prerequisite for following along. First, let us talk about Jupyter Notebooks. Jupyter Notebooks are interactive documents that allow you to write and execute code, visualize data, and document your workflow all in one place. They are widely used in data science and machine learning projects. Next, we will cover how to create a notebook using Vertex AI Workbench. Vertex AI Workbench provides a managed environment for running Jupyter Notebooks directly on Google Cloud, making it easy to scale resources and collaborate with your team. You can also add additional frameworks and libraries to your Workbench environment. This flexibility allows you to customize your setup with the tools and packages you need for your specific machine learning tasks. Finally, we will discuss best practices for securing your notebooks on Google Cloud Platform. Remember, Google frequently updates its products, so if you notice outdated information, please contact Shapingpixel@gmail.com.
For data and machine learning professionals, Project Jupyter has become a go-to platform for interactive and collaborative computing. But what exactly is Project Jupyter, and why is it so widely used in the data science community? Project Jupyter is a collection of open-source tools that make it easy to develop and execute code, process and analyze data sets, and share results. It is especially popular for data visualization, data cleaning, prototyping, and machine learning. One of the most popular tools is Jupyter Notebooks, a web-based application for creating and sharing documents that contain live code, equations, visualizations, and narrative text. Data scientists use notebooks to document workflows, reproduce results, and share insights. Jupyter Lab is the next-generation interface for Jupyter Notebooks. It offers a modular, extensible workspace where you can arrange multiple notebooks, code editors, and terminals in a customizable layout. Jupyter Lab also integrates with Git for easy version control. If you work with multiple notebooks or need advanced workspace management, Jupyter Lab is recommended. For single notebook tasks, Jupyter Notebooks are sufficient. Both tools empower data professionals to work efficiently and share their findings.
Vertex AI Workbench is a managed Jupyter environment designed for machine learning on Google Cloud Platform. It builds on Jupyter Lab, adding features and integrations that streamline your entire machine learning workflow. With Vertex AI Workbench, there is no need to set up infrastructure or install software. In just a few clicks, you get a pre-configured environment that automatically updates itself. Workbench is also highly scalable, letting you choose from a range of machine types, disks, GPUs, and TPUs. You can easily adjust resources as your project grows or changes. Vertex AI Workbench minimizes downtime by allowing you to create multiple instances across different regions for redundancy. Integrated version control ensures your code and models are always backed up. Security is a priority with role-based access control and compliance with Google Cloud Platform security standards, making it suitable for regulated industries. Seamless integration with Google services means you can import data from cloud storage or BigQuery, track experiments, and even run notebooks as steps in Vertex AI pipelines. You only pay for what you use, with options like sustained use discounts and automatic shutdowns for idle instances. Alternatives include Compute Engine, Dataproc clusters, or Collab Enterprise, but Vertex AI Workbench offers a balanced, efficient solution.
Vertex AI Workbench is a powerful platform for building and training machine learning models, but without proper security, sensitive data can be at risk. Let's cover the best practices for keeping your workbench secure. Start by limiting user access. Always follow the principle of least privilege, granting access only to those who truly need it. Use identity and access management, or IAM, to control permissions and consider enabling multi-factor authentication for extra protection. Only allow users to perform actions necessary for their roles. Reduce your attack surface by disabling public IP addresses on Workbench instances. Employees can connect through a virtual private network or VPN instead of exposing resources to the public internet. Add firewall rules and use virtual private cloud service controls for additional security. Protect your data both at rest and in transit. Disable file downloads when possible. Avoid storing private files in public cloud storage buckets and use encryption in access controls. Implement data loss prevention policies to further safeguard information.
Building machine learning models usually requires coding skills and knowledge of complex frameworks. This often leaves data analysts and engineers dependent on others to unlock insights from their data. But what if there was a simpler way? With Google BigQuery ML, you can create and run machine learning models using Google SQL, the same language you already use in BigQuery. There is no need to install extra software, set up development environments, or learn a new programming language. If you have a Google Cloud Platform account and NoSQL, you are ready to start. For example, you can predict the body mass of penguins based on characteristics like species, sex, island, and flicker length. Just write a select statement for your training data, add a create model command, and BigQuery ML handles the rest. BigQuery ML eliminates the need for exporting data or managing complex environments. Everything happens inside your data warehouse, skipping the entire extract, transform, and load process. This means faster results and less hassle for everyone involved. BigQuery ML supports many model types, including linear regression, logistic regression, clustering, and even AutoML. Plus, it integrates with Vertex AI, unlocking advanced features like anomaly detection and product recommendations. Introduction to Google Cloud Composer. Managing cloud environments can be overwhelming with countless complex and repetitive tasks. That is where workflows come in. A workflow breaks down big tasks into smaller, manageable steps, ensuring each one is completed in the right order for maximum efficiency. Workflows not only boost efficiency and reduce errors, but they also highlight opportunities for automation. By replacing repetitive manual steps with code, you free up valuable time for your team to focus on strategic thinking and problem solving, while automation scales with your workload. If you want to automate your workflows, Google Cloud Composer is a fully managed workflow orchestration service on Google Cloud Platform, or GCP. With Cloud Composer, you define workflows using code and trigger them manually, on a schedule, or in response to events. Cloud Composer is perfect for data processing, machine learning, and DevOps automation. For example, you can trigger database imports, submit Spark jobs, automate machine learning model training with Vertex AI, or streamline code deployment with Cloud Build and Cloud Run. Cloud Composer handles all infrastructure, supports hybrid and multi-cloud environments, and integrates with other GCP services. Manage everything from a single interface, making it easier than ever to orchestrate your cloud tasks efficiently. To use Google Cloud Composer, you first need to understand Apache Airflow, since Cloud Composer is built on top of it.
Let's break down the essentials you need to know. Apache Airflow is an open-source platform for automating workflows. It is free and supported by a large community, but requires manual setup, configuration, and ongoing maintenance if you use it directly. Google Cloud Composer is a managed service on Google Cloud Platform, or GCP, that simplifies using Airflow. It handles setup, maintenance, security, and scaling for you, but it is not free. In Airflow, workflows are called Directed Acyclic Graphs, or DAGs. A DAG is an ordered collection of tasks with dependencies, written in Python. Tasks can do anything from copying files to sending emails. A typical DAG file includes 4 sections: importing libraries, defining the DAG object, creating tasks, and setting dependencies. Scheduling options include daily, weekly, or custom cron expressions for flexible automation. Cloud Composer creates an environment using Google Kubernetes Engine, or GKE. It automatically scales resources and integrates with GCP services, while the Airflow scheduler monitors and triggers tasks as needed. When working with Cloud Composer and Apache Airflow, understanding their versions is crucial. Each version impacts your workflow, available features, and how your environment scales. Let's break down on what you need to know before you get started. Cloud Composer comes in 3 main versions. Cloud Composer 1 is now fully deprecated and unsupported. It ran both Airflow 1 and Airflow 2 with Python 3.8.12 and required manual scaling on a standard Google Kubernetes Engine cluster. Cloud Composer 2 is the current stable release, running Airflow 2 with Python 3.11.5 and uses an autopilot GKE cluster for automatic scaling. Cloud Composer 3 is still in preview, also running Airflow 2 and Python 3.11.5, but is serverless, hiding infrastructure details while supporting automatic scaling. When creating your Composer environment, you must also select an Apache Airflow version. This choice determines which DAG, or Directed Acyclic Graph, features are available. Composer environments do not upgrade Airflow automatically, so you need to monitor new releases and upgrade manually when needed. Before creating your Composer environment, carefully review which versions support the features and packages you require. Selecting the right combination ensures your workflows run smoothly and efficiently. Security is critical when using cloud services. As organizations rely more on cloud storage and processing, protecting sensitive data from cyber attacks becomes a top priority. Encryption transforms readable data into coded ciphertext that appears as random nonsense. Only authorized users with the right key can decrypt it. This process is a fundamental building block of data security, ensuring that even if attackers access your data, they cannot understand or use it. Data at rest refers to information stored but not actively used or transmitted, like files in cloud storage. Encrypting data at rest creates a second line of defense. Even if someone bypasses access controls and downloads files, without the decryption key, the data remains useless. Encryption also prevents unauthorized internal access and ensures data integrity. Data in flight means information being transmitted, such as uploading files or sending emails. Encrypting data in flight protects against eavesdropping and interception, especially over public networks. Without encryption, attackers can capture or even modify sensitive information using tools like packet sniffers. Data in use is information actively processed in memory.
Encryption is the process of transforming readable data into unreadable code to protect information. Most encryption methods rely on a key generated by a pseudo-random algorithm to scramble plain text into ciphertext. Without the correct key, decrypting the data is nearly impossible. Symmetric encryption uses the same key for both encrypting and decrypting data. For example, if you want to send an encrypted email, you generate a key and securely share it with your recipient. Both you and your recipient use this single key to encrypt and decrypt messages. Asymmetric encryption, on the other hand, uses two different keys, one for encryption and one for decryption. If you use asymmetric encryption, you generate a pair of keys. You share the decryption key with your recipient, allowing them to read your messages, but not to send encrypted messages back without their own key pair. Symmetric encryption is simpler, requiring only one key, but anyone with that key has full access. Asymmetric encryption is more flexible, letting you control who can read or write messages. This is especially useful for secure communication with unknown or untrusted parties, like logging into a website. Encryption keys can also create digital signatures, which verify the authenticity of data. With asymmetric keys, only the private key holder can sign files, while anyone with the public key can validate the signature. This ensures data truly comes from the claimed source. When working with data, understanding how information moves and changes is essential. 4 key processes help manage this flow: EL, ETL, ELT, and ETTLT. Let us break down what each of these terms means and why they matter. EL, or extract and load, is the simplest approach. Data is extracted from various sources and loaded directly into a target system, such as a data warehouse. There is no transformation step at this stage, making EL fast but limited in terms of data quality and analysis readiness. ETL stands for extract, transform, load. Here, data is first extracted, then transformed for analysis, and finally loaded into the data warehouse. ETL offers more control over data quality and security, but this comes at the cost of slower loading and less flexibility for future analysis. ELT, or extract, load, transform, flips the process. Data is extracted and quickly loaded into the warehouse, then transformed within the warehouse itself. This method prioritizes speed and flexibility using powerful warehouse tools for transformation. ETTLT, or extract, transform, load, transform, combines the strengths of both ETL and ELT. It allows for initial data preparation before loading, followed by deeper transformations inside the warehouse, balancing speed, flexibility, data quality, and security.
Hello and welcome to this new video. In this video, we're going to cover some important real exam question answers for Google Cloud Certified Associate Data Practitioner Certification Exam. So before going to the question answers, we request you to kindly subscribe to YouTube channel if you're not already a subscriber. And these question answers PDF is also available to download from shapingpixel.com website. The full link will be in the description. So each question in this video will be played for 1 minute without sound. If you think it's too slow or fast, use the YouTube audio settings to slow down or fast forward the video. Let's jump on to the questions.
Thanks for watching. If you haven't subscribed to our YouTube channel yet, we'd love for you to join our growing community. Just hit that subscribe button. Want a downloadable PDF of these questions and answers? You can grab it from our website, www.shapingpixel.com. Full link is in the description below. Happy learning!